All right, we're going into Unit 4, Chemical Reactions and Stoichiometry. So we have learned about the periodic table and some of the patterns on the periodic table. We're going to learn how those patterns guide the different types of reactions that occur in chemistry. And of course, we're going to quantify those amounts of reactants forming products in a balanced chemical reaction in this field called stoichiometry. So that is the basic synopsis of this whole unit, is understanding how chemical reactions can be quantified in stoichiometry. This is an extensive unit, and so continue on reading and filling in the blanks to make sure you're getting the whole story of this unit. We'll move on forward and we will go through the concepts as well as the calculations involved in this unit. All right. Our first topic is balancing chemical equations and identifying reaction types from that. So you've learned back in middle school that you have a chemical reaction oftentimes that looks like this. The layout has an arrow. So your reactants is on the left side, the products is on the right side. There are several ways we know a reaction has occurred, and we call these driving forces or evidences of a chemical reaction. And so there are 5 different types of evidences. Now, note, color change is not an evidence. You can put food coloring into water and that is not forming a new substance. We're looking for where we're forming a new substance from what we have originally in the reactants. So forming new substance in the product from the reactants. So here's the listing of them. There's the formation of a solid or precipitate, formation of liquid, usually water, and then formation of a gas. So these are all the 3 states of matter: solid, liquid, and gas. Then we get into light. Production of light is a evidence of a chemical reaction occurring, as well as temperature change. Sometimes the temperature change could be an increase in temperature as opposed to a decrease. So any kind of increase or decrease leads to a chemical change. So what's the difference in subscripts and coefficients? Subscripts is how we connect atoms together in a compound. You have been putting subscripts in to neutralize your ionic compounds oftentimes. And when you put a subscript in, you're just showing how they are bonded and connected together in that compound. Coefficients are used to tell you how many of those substances, compounds there are in a chemical reaction. We add it when we're balancing chemical equations. We add coefficients. Physical states of matter. There are 3. Because driving forces involve physical states of matter, it's important for us to identify physical states of matter. Solids is always denoted by S, liquids L, gas G, and aqueous is another state of matter, and it's usually an ionic compound dissolved in water. So the word aqueous is suggestive of an ionic compound. Now, it could also be a covalent compound, but that covalent compound is usually an acid. So it could be an acid or dissolved in water. Now, the word aqueous has the word aqua in it, and aqua is water, so that is suggestive that we're in the medium, the solvent is water. So let's go ahead and review this whole physical states of matter. We know that the stronger the intramolecular force, oftentimes you're seeing solids as the state of matter. Whether it's covalent network bonding or metallic bonding or ionic, it's solids. Now, certain solids are soluble, ionic solids are soluble, and so when they're soluble, they dissolve as ions. If they're insoluble, they stay as a pure solid. Okay. Now, intermolecular forces work for covalent compounds, and covalent compounds there's two types. There's polar covalent and nonpolar. Usually your polar covalents are usually your solids, low melting point solids, or volatile liquids. Your nonpolar covalent, because they're held so weakly together by London dispersion forces, are oftentimes your gases. So this is really important. Going back to what we learned in Unit 3, where we understood intermolecular forces and the forces of attraction between particles as well as within particles. This is important for us to understand these driving forces in a chemical reaction in the end has occurred to forming a new substance. So very important to take what you've learned and translate it into this next unit. So the first question is, do solids often have intra or intermolecular forces? And we know that solids are held together quite tightly together. Oftentimes, not always, but oftentimes, it's intramolecular forces that solids have. And to explain that is because those intramolecular forces are stronger forces than the intermolecular forces. So intramolecular forces are stronger than inter. And so that's why those particles are held much more tightly together because they have stronger force. What type ionic covalent metallic covalent network tends to be liquids and gases? And we said that those are intermolecular forces, and that would be your covalent compounds. So covalent compounds tend to be tend to have intermolecular forces. And just a reminder of the intermolecular forces that we've learned already. There is London dispersion. There is dipole-dipole forces and hydrogen bonding, and of course ion dipole. And so those are your review of your intermolecular forces. And these are weak forces. And those weak forces that hold between these particles will oftentimes lead to them, covalent compounds, being liquids or gases. Stronger forces within or between bonding particles, the closer, of course. This is Coulomb's law. Retaining physical states more like a solid than a liquid or gas. Taking a look at the periodic table that's in my classroom right here, and looking at the key legend, the color key legend. Black means solid, red means gas, and then blue means liquid. These are elements, they're pure substances. And so we can state a couple of claims based on what we see. All that's black are your metals, oftentimes. Your reds are your nonmetals, and so these are bonded covalently, whereas these are bonded metallically. So that's why metals tend to be solids, covalent compounds tend to be gases at room temperature. And room temperature is 25 degrees Celsius, so we always do note what temperature we're looking at when we're looking at states of matter. The diatomic molecules are basically reviewing the idea that you have di means two, of the same atoms bonded together in a non-polar covalent bond. So there are 7 of them, and they make this number 7. So there's N2, O2, F2, Cl2, Br2, and I2. There's some exceptions, S8 and P4. What do you notice about the physical states of the halogens? So I'm just strictly looking at the halogens, which is this last group, or group 17 right here. Noticing as you go down the group. If you notice you're becoming, or the forces of attraction are getting stronger and stronger, that's why you start off as a gas, leading into a liquid, and of course a solid going down this group, which means the forces are getting stronger. the question is why? Well, from what we've learned, all of these substances have what are called London dispersion forces. So all the halogens have LDF forces because they're nonpolar covalent. And with that, nonpolar covalent compounds, London dispersion forces work through electrons, creating temporary dipoles in the structure, thus forming temporary attractive forces between particles. So the more electrons you have down here, the stronger those temporary dipoles will be versus the less electrons up here. And that's why chlorine and fluorine, both these two gases, are gases, whereas these two iodine and astatine are both solids. And then of course bromine is a liquid. So we can see the trend as we go from gas to liquid to solid going down that group. And that's all because the more electrons lead to stronger forces and stronger London dispersion forces. All right, let's go into balancing chemical equations. When we balance chemical equations, we add coefficients until reactants and products contain equal number of atoms of each element. And why we do that is because of conservation of mass, which states that mass can neither be created nor destroyed in a chemical reaction. And because of that, we do want to make sure we understand how to do that using this example. If you look at this example, you have one water molecule, which you see here, one hydrogen molecule, and one oxygen, double bonded here, of course. It's a diatomic molecule. Now, with that, you'll notice that there's this arrow separates the reactants and the products. On the product side, there's 2 oxygen atoms. There's only one here. So is mass conserved? No, it isn't. So we're going to have to find a way to conserve mass. So we need another oxygen. But we can't just add oxygen. Oxygen comes as water here. So we have to add another water molecule. That will give us 2 oxygens. Now in doing so, now I've unbalanced the number of hydrogens. Now I have 4 hydrogens on one side and 2 on this side. So I'm going to have to add another hydrogen molecule. And so when you're balancing equations, you're adding coefficients. And these are the coefficients that you're adding here. Right here, right here, and of course there's only one here, but we don't need the one there. We don't need to write one. But what you're doing is you're adding more of that substance to balance the equation. You're not just adding that particular atom of that given element. You're actually adding more of the substance with the atom of that given element. And so now we have a balanced equation. And the way we check is we see how many we have. 2 times 2 is 4 hydrogens. 2 times 2 here gives you 4 hydrogens. So there's 4 hydrogens on both sides of the equation. 2 times 1, there's only 1 here of the oxygen in water, so that's 2 oxygens. And of course, 1 of a diatomic molecule of oxygen means there's 2 oxygens. So you can actually account for the conservation of the masses of each of the given elements that are in this chemical equation. So this is unbalanced, and this is the balanced form of it. We'll practice through. Let's look at example 1. In example 1, first, one of the things we want to make sure we do is we identify the states of matter. And why we identify the states of matter is because the formation of a solid, liquid, or gas, or heat, or some temperature change tells us whether a reaction has occurred. So that's part of this example, is to practice our states of matter. And if you remember, depending on the type of substance and the bond type, that will discern the state of matter. Within, of course, some substances are more difficult to tell, especially the covalent substances, but certainly ionic, metallic, and covalent networks are solids. Most of them are solids at room temperature. So the first one is hydrogen. We know hydrogen is H2 is covalently bonded, nonpolar, so we assume it's a gas at room temperature. And we are assuming it's at 25 degrees Celsius. Oxygen, also a gas at room temperature. If you look at my periodic table, it tells us just that, red and red. So oxygen and hydrogen are red. So that's why I took a picture of the periodic table so that we have reference to that. Now water is polar and it engages in hydrogen bonding. So from that we can tell that it's a liquid at room temperature. So L is for liquid, G is for gas, S is for solid. Now let's go ahead and balance the equation. I have two hydrogens on the reactant side and two hydrogens on the product. So it looks like the hydrogens are balanced. Oxygen, I have two on the reactant side and one on the product. So I'm going to need to add another water molecule. Adding another water molecule gives us now two water molecules, which is two oxygens in the end. So there's two oxygens. That balances out the two oxygens. Now, of course, that impacts the hydrogens, so I'm going to have to go back and rebalance the hydrogens. So there's 4 on the product side and 2 on the reactant, so I know I'm going to put a 2 right here to get 4 on both sides. So notice I'm not putting any subscripts, so I'm not changing these numbers down here. I'm only putting coefficients to balance this reaction out. So what you would have gotten if you put a 2 right here for the oxygen so that you can balance the oxygen was a different substance called hydrogen peroxide rather than water. And that's why you only put coefficients. Coefficients doesn't change the substance. Putting subscripts will change the substance. So I'm going to put a 1 here just to affirm that it is a coefficient of 1. Looking at the reaction type, pull out your blue sheet of paper. Your blue sheet of paper will tell you your reference to the different reaction types. And when you reference that, you'll see that this reaction looks like it's being a synthesis because two simple substances combine to make one substance. So it is a synthesis reaction. All right, moving on to letter B. Letter B, I'm going to do the states of matter first. This is silver nitrate is ionic because it's made up of two ions, silver and nitrate ions. So this is going to be solid normally. However, because we're in water, as you see right here, that means that ionic compound is going to be soluble. And so we're going to say it's aqueous. Likewise, magnesium chloride right here is also an ionic compound in solution, so it's aqueous as well. And so we start off with two solutions of your two ionic compounds. And in terms of the products, this is where we're going to pull out our solubility table to figure out what the state of matter for each of these products. According to our solubility table, look at your pink sheet now. You can see that silver chloride, in fact, is insoluble. Insoluble means it doesn't dissolve, which means silver chloride is going to be a solid. Magnesium nitrate is soluble, which means it's aqueous. So in the products, you have to look at the solubility table, which is your pink sheet. It's on your pink sheet. It's a nice big chart that allows us to know whether a substance will become, or the product side of it is going to be soluble or insoluble. In other words, is there going to be a driving force? And in this case, the driving force is a solid forming here. And that indicates a reaction has occurred. And this is a double replacement reaction. And how I know that is I see, and I'm going to abbreviate that because I have very limited room. And I can see that these two ions right here, the cations of these two ionic compounds are switching places. And upon switching places, and I'll show that swap, the cations switch places. Silver is now with chloride and then magnesium is now with nitrate. And so that's double, both the silver and the magnesium are replacing each other. Let's go ahead and balance this equation out. There is 1 silver on the reactant side, 1 silver on the product side. There's 1 nitrate. I'm going to treat the whole ion as a whole grouping because I see the same ion in the product. So there's one nitrate ion here. There's 2 nitrate ions here, so I'm going to need a 2 coefficient right here. And that's precisely what I'm going to do. Put a 2 right there. That gives me 2 silvers. So I like to jump from 1. If I was focused early on the nitrate to balance it, now because I put a 2 here, it's going to impact the silver. So I jump over to the silver immediately so that I can balance the silver over here. And so I need a 2 coefficient right on the product side in front of silver chloride. And then now I count my magnesium. I jump now to magnesium. I see 1 of each on both sides, so they're balanced. Chloride, I see 2 chlorides, and I see 2 chlorides. Notice the 2 in front here really distributes to the 2 chlorides here, so it's balanced. Okay, now let's go ahead and continue on with the next. Now this is a nonpolar substance. Nonpolar substances are usually gases, and that's precisely what methane will be. Oxygen is a gas, carbon dioxide is a gas, and water, in this case, is going to be a gas. And why it's going to be a gas is this is a combustion reaction. Combustion reactions oftentimes release heat and light. So these are the symbols for heat and light. Even though it's not in this reaction, I know that this combustion reaction will release both heat and light. And those are your symbols for heat and light. Alright, let's go into balancing. 1 carbon here, 1 carbon here, so they're balanced. 4 hydrogens here, 2 hydrogens here, so I'm going to need to put a 2 in front of the water. Giving me, now I'm ready for oxygens. I do oxygen last because oxygen is really all over the place. In other words, it's in different substances. It's here, here, and here. So I balance it last. And plus there's an oxygen right here by itself. I can put any number and it won't impact any element except for that oxygen. So I am going to balance oxygen last. There's 2 right here, plus another 2 right here. That gives us 4. So we go over here on the reactant side. I need 4. That means I need a coefficient of 2. Let's move on to letter D. In letter D, let's go ahead and assign the states of matter of each of the substances. The first substance is an element, so we look in the periodic table of elements, and we see that sodium, the element, is black, and that means it's a solid. So I'm going to designate sodium, which is bonded metallically, as a solid. Water bonded covalently. We know the state of matter of water. It's polar, covalent, and has hydrogen bonding, which oftentimes means that water is a liquid. And then we see the formation of an ionic compound. And because we're in water, we can determine whether this ionic compound is either soluble or insoluble. And we look at the solubility table to discern that. And from doing so, I look at the solubility table and I see that it says the letter S, which means it's soluble. And the designation for soluble substances is aqueous. So I'm going to put AQ. Aqueous means the substance dissolved in aqua, which is water. So this ionic compound dissolved in water. Hydrogen is an element, as you can see right here. It's just a single element. Well, it's diatomic because it needs to bond with itself to be stable. But we look on the periodic table to discern what the states of matter of single elements are at room temperature. And it's red, so that means hydrogen is a gas. Now let's go ahead and figure out what's happening in terms of, let's balance it. And accordingly, we count that there is 1 sodium, 2 hydrogens, 2 hydrogens plus 1 gives you 3, so there's 3 hydrogens on this side. I'm going to need to add more hydrogens. I'm just going to add one more for now. And in doing so, I get 4 hydrogens on this side, plus that changes the oxygen, so there's 2 oxygens and 4 hydrogens. But let's focus on the hydrogens. I have 2 hydrogens here and 1 here. I need 4, and I know that I doubled up the oxygen too, so it'd be nice to put a 2 here. That gives me a total 4 hydrogens as well as 2 oxygens. So I really did do both the balancing of oxygen and hydrogen at the same time. And so that changes. Of course, putting a 2 in front here changes the sodium. So I have to go back and recount sodium. And it looks like I'm going to have to put a 2 coefficient right there, leaving me with a 1 coefficient right here. So this is if you look at this reaction, you can see that it's single replacement. And how you know is you see a single element right here, sodium, and then you see a compound that's made up of 2 or more elements, in this case hydrogen and oxygen. So this sodium is going to replace something in this water molecule, and it looks like it's going to replace a hydrogen, because if you look at who's single now in the products, it is hydrogen, which means hydrogen got kicked out. But the question is, how would hydrogen get kicked out of water? So we're going to look at water on the side, and water is H2O, which means water can be written also, when you draw the structure, you'll see that water looks like HOH. It's bonded like that. So it has the same formula if you compare it. Notice the 2 hydrogens, and the 1 oxygen, Now water, you don't know yet, but water ionizes into 2 specific ions. And you can see it when you write it this way right here. You can see the hydrogen ion and the hydroxide ion. And so I'm going to rewrite that water with those 2 ions in mind. That way I can say, okay, if sodium were to replace one of these 2 ions, what would sodium replace? You're right if you said it's the cation, because sodium could only be a cation. And so that's what sodium's going to do. It's going to replace the cation, forming sodium hydroxide here. And of course, hydrogen gets kicked out as a diatomic molecule called H2. So this reaction is a single replacement, and whose replace is in fact the hydrogen ion. And we call that a single replacement, abbreviating the word replacement, and it's cationic because the single element replaced the cation. Alright, go ahead and pause and finish up the rest of the problems, moving through, and I'll show you all the answers to the rest after you've had the chance to practice. Practice is very important through this. Alright, hopefully you've had the chance to work through all of these problems all the way to I, and you can check your work with that. Now let's go to word equations. Now if you need to get out your lime green sheet, go ahead and do that. You should know how to name these compounds pretty easily given all the quizzes we've taken last semester on it. This is why we've been doing all those quizzes, because now you have to take equations, word equations, and be able to translate it into chemical equations. Okay, so starting off with water, and it's a liquid, and it reacts to yield, which means there's an arrow right here. So there's my arrow, and it's reacting to yield 2 gases. There's oxygen, and that's a gas, plus hydrogen gas. Now let's go ahead and balance. I'm going to balance it in black so it'd be easier for us to contrast. There's 1 oxygen here and 2 oxygens here, so I'm going to need a 2 coefficient. And then that gives me 4 hydrogens, and that means I want 2 right here. So it's 2, 1, 2 ratios here. Alright, the next one would be copper. I'm going to start off with copper solid, and copper is a metal, so Look at my periodic table in the previous page. It's in black, so it's a solid. It's bonded intramolecularly, and it reacts with sulfuric acid. Now, you're going to have to go back to your naming system and practice sulfuric acid. And if you did this, you would have gotten it, or if you've put H2SO4, that is the correct formula for sulfuric acid. And it produces copper 2 sulfate, so CuSO4. And I'm going to have to look at my solubility table to know, my pink sheet, to know whether this ionic compound is soluble or not in water. Oh, sorry, I should mention, all acids are aqueous. If you see the word acid, it couldn't be an acid unless it's in water, okay? So all acids are aqueous. And then the substance that is going to form is sulfur dioxide, and it says it's gas. So sometimes the word equation will already tell you what the state of matter is. I look at my solubility table and I look up copper and sulfate, copper ion sulfate, and it looks like it's soluble. So this is going to be aqueous. Now I balance this whole equation, and balancing this whole equation, I see that there's 2 hydrogens. Oh, I'm missing water. That's why it doesn't look quite balanced. So let's put water in. It says water, so plus water. I'm going to need some room to put a coefficient possibly. And that water, because it doesn't say water vapor, that water is a liquid. So now I'm going to balance this equation. How I knew I was missing water was because I didn't see the hydrogens. And I was like, wait, where could it be? It means I'm missing it somewhere. Okay, so I'm going to treat sulfate as a whole group here. And it's because there's sulfate here. But then it's also divided over here. So I guess I can't treat it as whole group. In other words, I'm going to have to break up sulfur and oxygen and count them separately, okay? Not as a whole group. Okay, so 1 copper, 2 hydrogens, 2 hydrogens. I'm going to leave oxygen last. 2 sulfurs right here. So I'm going to start off by putting 2 sulfurs, or 2 of the acid. And that forces me to put a 2 right here for the hydrogen. And now I'm going to hope that the oxygens work out, because this is a difficult one to try to balance if we're only limited with different substances that have these elements, or very limited number of substances having these elements. So 8 oxygens, 4 plus another 2 plus another 2 gives me 8. Perfect. So this equation is all balanced. And this is a single replacement reaction, but there's also, I'm going to add another. It's also going to lead to some decomposition as well. So decomposition as well as single replacement reaction. You won't oftentimes see 2 reactions in our class. When you get to a higher level, you will see multiple reactions. All right, let's move on to the next letter L. Hydrogen gas reacts with nitrogen monoxide gas to yield water. And because it says water, that's a liquid, and nitrogen, and it tells us it's gas. The problem itself tells us it's gas. Let's go ahead and balance. There's 2 here of the hydrogens, 2 here. Only 1 nitrogen and 2 nitrogen here, so I'm going to need a 2 coefficient right here. That gives me 2 oxygens, so I'm going to need a 2 right here. That changes the hydrogens to 4 on the product side, so I'm going to need a 2 coefficient right here. So it's a very dynamic process. You're not always done when you're done with one element. You might have to go back and rebalance that element, depending. A go ahead and pause this video and work through the rest of the problems. I do want to correct one of the answer key, and that would be this one right here, letter N, and I'll go ahead and put the correct coefficients in so that you can check when you're ready to check. Again, please make sure you're practicing this. The practice is really important. So this is a ratio of 2, 3, 2, 3. Okay, we did jump the gun a little bit in terms of understanding the reaction types, but this is your layout of the different reaction types. It's hopefully something's a little off here, but in terms of the reaction types, this is your various general equations. Synthesis being two things combining to form one. Decomposition is one substance breaking down into simpler substances. Single replacement is when an element somehow replaces something in a compound, so a similar element. So if the element can only be a cation, it will replace only the cation. If the element is an anion, or like oftentimes an anion, so that element will replace the anion in the compound. Combustion is usually a hydrocarbon reacting with oxygen to form carbon dioxide and water. And then a double replacement is really two ionic compounds usually switching places to form new compounds. So this is a very good chart and description of what we just described of the different reaction types. I want you to study these reaction types and make sure you can identify the driving forces, which is where there's chemical change, a new substance is forming. So solid, liquids, temperature change, or light produce is what we're always looking for. Any of these. It could be one evidence or it could be all 5 evidences. So it really is important that a reaction exhibits at least one of these evidence to know that a reaction has taken place. Now, single replacement reactions require us to look at something called the activity series. This is located on your blue sheet, so pull out, hopefully you still have it out. Your blue sheet will describe which element will replace which element. And if you notice, the alkali metals, which are up here, or the alkali earth metals, are really more reactive than all your precious metals. Your precious metals are things like gold, silver, platinum. These are metals that you use for jewelry. So hopefully you can understand why you don't want them to be very active. You would rather them to be the less reactive, because that's why they become precious metals, because they don't react very easily. But your alkali metals, which only have 1 valence electrons, tend to be very reactive. And your alkali earth metals are also quite reactive, and that's why they're on top here. So only if you're on more reactive, in a single replacement reaction, the element that's single will only replace a similar element in the compound if it's more reactive. So you're looking at this chart to know who's more reactive and how to see if there's a replacement for that in the compound. So this is cationic right here. This whole column is where they're all cations. These elements can become cations. Whereas this column is your anionic. So these are all the halogens, the activity of the halogens. We will go through a few of these problems. Of course, you're going to go through the others afterwards, but we will apply this activity series to single replacement reactions only. So here's your first single replacement. You've got an element. We want to know if that element can replace the silver in this ionic compound. Now notice this copper can only replace the silver. It cannot replace the nitrate. If copper replaced the nitrate, what you end up with is silver, which is a cation, bonded to copper, which is another cation. And so that's impossible to have. 2 cations repel each other, not attract each other. So what you're going to see is an equal or similar replacement. So copper will replace a metal. The metal is silver. So to know if copper will replace silver, you look at the activity series, and copper's right here, silver's down here. It looks like copper's more reactive than silver, so that's why copper will kick silver out and bond with the negative nitrate ion. And so a reaction will take place, and we want to predict the products from that. So when copper reacts to replace the silver, copper takes on its most common charge, which is +2, which means this nitrate is going to be, there's going to be 2 nitrates to neutralize that +2 charge. And this is aqueous when I look up the ionic, or I look up my solubility table. I always look up, when I see an ionic compound forming, I always look up my solubility table to see if it's aqueous, soluble, or insoluble. And that way I can designate the states of matter as aqueous or solid. Now we see that silver gets kicked out, and because silver is a solid, you write solid there. You don't have to balance this. This is only asking you to predict the products. Who is the driving force for this reaction? Well, you see a solid forming from this reaction, so silver solid is the driving force for this reaction. Let's move on to the next. Now you see reversal, which is, will silver replace copper? Well, silver is below copper, so silver as a single element will not replace the copper. So we call this no reaction. So NR is going to be my abbreviation for no reaction. Now we go to the next. Will copper replace its similar element, which is iron? So it looks like iron's higher than copper, so copper cannot replace iron, which means NR again. Will iron replace copper? And it looks like iron will replace copper, and when iron replaces copper, iron takes on its common charge, which is +3. And I look up the solubility table, the pink sheet, and I see that iron 3 nitrate is soluble, which means it's aqueous. Who gets kicked out? Solid silver. All right, I'd like you all to pause the video and work through the rest from E to J, and then you can check your answers as you practice and work through the rest. So obviously, knowing the solubility or knowing the states of matter is very important to know whether a reaction has taken place or not. In other words, it helps us to understand the driving forces. The driving forces including solid, production of a solid, liquid, or gas, and then also temperature change or light formation. So those driving forces helps us to understand whether a reaction has taken place or not. And thus, we've been practicing quite a bit, putting states of matter in so that we can understand whether a reaction takes place or not. So once again, pull out your pink sheet, look at your solubility table. We will now look at how ionic compounds that are formed in double replacement or single replacement reactions require you to look at your rules to determine whether that ionic compound is soluble or insoluble. If it's soluble, we designate it as aqueous. So I am going to highlight this idea. Okay, soluble, aqueous. Insoluble, solid. So you really need to make sure you see that difference. So let's go ahead now and do that. This is a very simple idea. So all you're looking at is that pink sheet, solubility rules, and we know that these are all going to be in water. We're assuming they're on water, and we're predicting whether they're physical states of matter, dependent on whether the substance is soluble or insoluble. So looking at my pink sheet, I have it in front of me. If I looking at silver and chloride combined together, I see that it is insoluble, which means it's a solid. Sodium chloride, looking it up, taking a second to look it up, and I see it's aqueous. Sodium hydroxide, looking it up, it's a pretty easy chart. You just combine your cation with your anion, and you will see whether that substance is soluble or insoluble. Of course, this is sodium hydroxide is soluble. Barium hydroxide is insoluble, and so it's a solid. Pause and go ahead and work through the rest really quickly and check your answers with my answer key. Okay, so we're going to get into what is called the net ionic equations. The net ionic equations are pretty much a derivation of the balanced equation. However, it allows us to focus on all the species that are involved in a chemical change between the reactants and products. So you're going to see just that are the pieces that really all the species that make up the driving forces, which oftentimes are which is notably what tells us a reaction has taken place, a chemical change has taken place. So, we know dissociation is when ions in an ionic compound, what it does when it dissolves, often in water. In other words, when it's soluble. So when ionic compounds dissolve, like sodium chloride, usually dissolves into these two ions, separated by water. Now, you're going, this doesn't look like it's a balanced equation, and that's why the better way to write the dissociation of an ionic compound is to just really focus on the ionic compound and say that 1 mole of this ionic compound breaks up into these two dissociated pieces. Now, really, it's actually 3 dissociated pieces, 2 ammonium, 2 moles of ammonium ions, and then 1 mole of sulfide ion. So these are the 3 total dissociated ions that are coming off of ammonium sulfide. Again, we like to get rid of this water and focus on the ionic compound and the dissolved ions that make up the ionic compound. So what are substances that tend to dissociate? Solutions like ionic compounds oftentimes can be dissociated, and you tend to know that they're soluble because of the solubility table. Oftentimes, and of course, the word solution suggests that they're soluble. Acids are also always aqueous, so we put the word aqueous. Now, strong acids dissociate completely, and weak or strong bases. But strong bases, it's easy to tell that they dissociate completely because they're ionic compounds. Acids are harder to tell because they're covalent, and acids tend to look like covalent compounds, so you've got to watch out for them. Now, what do not dissociate are your solids, liquids, and gases, and certain acids. What kind of acids and bases? The weak ones. So there's a list on your lime green sheet. So if you look at your lime green sheet, it actually tells you about what are your strong and weak acids. So this information is on your lime green, and there's a listing of what's strong and what's weak. So you should look at that, and I will be giving you that information on any tests as far as whether an acid is strong or weak. All right, let's take a look at our first problem as far as working our way to what is called the net ionic equation. Just a reminder, net ionic equation, what it allows us to do is it's a derivative form of the balanced equation, but it focuses on the driving force and all the species that undergo a chemical change. So let's start off looking at an example. You've got ammonium sulfide and cadmium nitrate, okay? Cadmium nitrate. And so if you look at this reaction, it completely, hopefully, you can identify it as what is called a double replacement reaction. And so you're going to switch the cations and their placements. And when you switch their places, now ammonium, which has a +1 charge, I am still going to neutralize my ionic formulas. Now, ammonium with the +1 charge is going to be with nitrate, which I memorize as a -1 charge, and so they neutralize together very nicely, one of each ion. I know that ammonium nitrate is very soluble, so I'm going to call it aqueous. I look at my solubility table for that. Then I go into cadmium. Cadmium is with sulfide, and cadmium is a +2 charge, sulfide is a -2 charge, so they neutralize themselves really nicely. Looking at the solubility table for this ionic compound, it looks like this compound is insoluble, which means that's our driving force. Let's balance this equation as we normally do. So balancing this out, I see 2 ammoniums, so I'm going to put a 2 coefficient here. That actually helps to balance the nitrates because there's 2 nitrates here, 2 ammoniums and 2 nitrates. That really, putting a 2 in front really accounts for the 2. Cadmium, 1 cadmium, 1 sulfide, 1 sulfide. So this all looks balanced out. Really, it now looks balanced at this point. Let's go ahead and look at what to do when it comes to a net ionic equation. So the first thing you want to do is you first want to see what is soluble. And aqueous means the substance is, and it's ionic, you are to dissociate it. So aqueous, and this one also is aqueous, so, and it's ionic, so you are to dissociate it. This one's a solid, not to dissociate. This one's aqueous, ionic, dissociate. So this chart helps me to know what to dissociate and what not to. But really, essentially, the really big part of it is anytime you see something aqueous, you dissociate, unless it's an acid. Be careful of the weak acid. So I'm going to dissociate these. Now, dissociating ammonium sulfide, I'm going to dissociate it into 2 ammonium ions and 1 sulfide. Likewise, cadmium is going to be dissociated into cadmium 2+ and 2 nitrate ions. Notice these are all ions, okay? And notice they're ions that you recognize, some of which. I'm going to dissociate ammonium nitrate here into 2 ammoniums and 2 nitrates because there's a 2 coefficient here. And I won't dissociate cadmium sulfide because it's a solid. Now, upon dissociating them, I have this equation called the complete ionic equation. And complete ionic equations are all dissociating soluble salts are dissociated into dissolved ions. And that's exactly what you see here. All the ones that dissociate have been dissociated. Now I'm going to do something that is very similar to math. When you see 2 terms added, 2 of the same terms added on both sides of an equation, you can get rid of it. And mathematically, that's exactly what I'm going to do in this chemical equation. In this chemical equation, I'm going to get rid of what are called the spectator ions. Spectator ions are ions that appear at the beginning and they appear exactly the same in the end. So beginning and end, 2 ammoniums get cross-canceled. Or sorry, just canceled. I shouldn't say cross-canceled. Nitrate is also the same, so we're going to cancel them. And that means these 2 ions, the ammonium and the nitrate ions, are spectator ions. In other words, they don't change. They don't undergo a chemical change. So what's left are my 2 species that make up my driving force, my solid precipitate. And that's why this reaction is called the net ionic. It basically shows all the species that are involved in the chemical change. In this case, all the species that make up cadmium sulfide. Cadmium 2+ and sulfide 2-. So when you draw all of this, microscale wise, you are to draw each of the reactants. In this case, however many of them, I have 2 ammonium ions and 1 sulfide ion. And basically it's going to look like what you see here in the complete ionic equation, okay, which is this step right here. But they're going to be in separate beakers before you add them together. And so in the second beaker, I'm going to have cadmium 2 plus and 2 nitrate ions. This is illustrating what's happening. And so now I know that my cadmium and my sulfide ions are going to combine to form a precipitate. And so my precipitate is a solid. And I know very well that solids tend to sink to the bottom. And so I'm going to put the word solid in there to know that it's sunk to the bottom, leaving me with conserving, of course, all the rest of the substances as dissolved ions, leaving me the following dissolved ions. I know that I have 2 ammonium ions, and I have 2 nitrate ions. So notice how mass is still conserved. The 2 ammonium ions you still have in the product side. The 2 nitrates also in the reactant side is still present. The cadmium sulfide in the reactants, both reactants, are also conserved. So balance-wise, you should see conservation on the reactant side with respect to the product side. So always double check to see if the law of conservation of mass is adhered to. What I would like you all to do is pause the video and work through this problem on your own, and then also work on these problems following, these 2 example problems following. You will, after you unpause, you'll see all the answers there. Alright, so here are the answers. I do want to mention that for this question right here, when you add sodium iodide instead of potassium iodide, you'll see that the net ionic equation is the same as your had you added potassium iodide. So given that both will have the same desired precipitate with the same and the cation is irrelevant. In other words, this potassium ion and the sodium ion are actual spectator ions. You're not going to see that exchange of sodium or potassium for sodium to have an influence on the desired precipitate. I ran out of a little room, so be aware that I put a 3 in coefficient to show for the 3 barium sulfate precipitates on the microscale drawing here. Yeah, hopefully you can work through it and check your answers as you go through these problems. The mole concept has always been a very difficult concept for students to think of. And so I'm going to start off by talking about a similar unit to the mole as we use out in the world. And the word is dozen. So instead of saying, give me 36 eggs or give me 48 eggs, people would rather say, or farmers when they went to the store would rather say, give me 3 dozens or 4 dozens. And so the word dozen represents a unit, and the unit is 12 of something. A mole represents a unit as well, and that unit is actually Avogadro's number, which is 6.022 times 10 to the 23rd particles. Now, why do we use a mole? Because atoms are so small, and because they're so small to measure, we need a lot of particles to have a measurable amount. And so we have this unit called a mole, which represents a very large number of particles, 6.022 times 10 to the 23rd particles. A mole is actually based on the number of particles that are in exactly 12 grams of carbon-12. So carbon-12 becomes a standard for a lot of other measurements, like 1 AMU. We use carbon-12 as a reference for that. And just Likewise, we use carbon-12 to represent what the number of particles there are in a mole. Okay, there are three types of represented particles that you will come upon. And they're really named based on what type of substance it is. If it's a single element like you see here, copper, iron, gold, and sodium, we term that atoms. We can call them singly, in single units, they're atoms. Whereas their compounds, which are these two, covalent compounds, we call them molecules. And these are all nonmetals bonded together, makes a covalent compound. So we term that molecules. And now molecules can be broken down into atoms. Like for instance, one molecule of water has 2 hydrogen atoms and 1 oxygen. One methane molecule has one carbon and 4 atoms of hydrogen. So we can break molecules down into smaller units called atoms. Ionic compounds, ionic compounds are identified by metals with nonmetals. Ionic compounds are called formula units. In one unit, we call one unit of that ionic compound a formula unit. Of course, we oftentimes have multiple of these formula units of these ionic compounds to make what is called the crystal lattice structure. Now, we can take a formula unit and break it down into their separate ions. Like, for instance, in sodium chloride, there's 2 separate ions. There's a cation, sodium ion, and then there's an anion, chloride ion. If you look over here, magnesium chloride has 1 magnesium 2+ ion and 2 chloride ions. So you can actually break these ionic compounds into pieces called ions. So, and this is a very nice visual to help us to see how substances look when they're a molecule of water, a mole of water. This is what a mole of water looks like, versus a molecule of water. And notice in this, there's a lot of water molecules in here. And the number of water molecules that are in here is actually 6.22 times 10 to the 23rd molecules of water. So this is what 1 mole of water looks like. What does 1 mole of copper look like? It actually looks like this wire here, this thread of wire, this roll of wire. And that roll of water has 6.022 times 10 to the 23rd atoms, because this is copper, a single element. Now this last one, a mole of sodium chloride, which is salt, has 6.022 times 10 to the 23rd formula units. So notice I'm using these different terms for these representative particles. Now you're going, how am I going to count out this number of particles for water as well as for a solid like copper here, or even a solid like sodium chloride? How do I count this many particles? Instead of counting them, we weigh them. And so what I want you to do is I want you to look at the periodic table and find the average atomic masses of 2 hydrogens plus 1 oxygen. We're doing what is called the molar mass. We're weighing them out. And when you add them up, 2 hydrogens and 1 carbon, 2 hydrogens and 1 oxygen, the 2 hydrogens is, each hydrogen is 1.01 grams. Plus 16 grams for the oxygen. So these are your hydrogens and this is your oxygen. You add them up together and you get 18.02 grams per 1 mole. So this is what is called molar mass. And that's how we actually massed out this amount of a mole of water. We tared out the container that holds that water, so we can zero out that container, and then we poured enough water until we hit 18.02 grams. Likewise, for copper, what we did was the same thing. So look at your periodic table and find copper's molar mass. Its molar mass, as written on the periodic table, is 63.55. And literally, I put copper on the balance and weigh it out until I get 53.55. So these masses, we look at the periodic table using the average atomic mass. Sodium chloride, the same thing. Each sodium is 22.99 grams for each sodium. And then I'm going to add it to a chlorine, which is 35.45 grams. And when I add those two together, I get 58.44 grams per 1 mole. And so all I do is just put this on the balance, tear out the object that's going to hold that salt, container or whatnot, and then just pour salt until it hits 58.44 grams. So weighing it out really prevents us to have to count these particles. It's impossible to count these particles. We weigh it out and we know that really represents a mole of that particle or of that substance. Alright, we're going to practice with these represented particles because they can get really tricky and knowing them is really important. So if I have a metal and it's a single element, I know that that metal is called atoms. So the unit that we use to represent that particle is an atom. The second one is a covalent compound, and covalent compounds are the words molecule. And then the next one is an ionic compound, and so I'm going to use the word formula unit. So practice knowing which word and terminology to use for each of these scenarios, okay? Pause and work through the problems and check your answers afterwards. This is a very important chart for us to do what is called mole conversions, and we're going to do that after we calculate molar mass. But let me go over this. So we now know that a mole of a substance has 6.022 times 10 to the 23rd atoms, molecules, or formula units, depending on the substance we're looking at. Now, a mole or a formula unit, which is abbreviated FU, a mole of something or a formula unit of something can be broken down into atoms or ions, depending on the substance. So we will have to look at the substance, and that's why there's a question mark. So it depends on that substance. A mole of a substance also has a certain mass, and we find the mass from the periodic table. We call that molar mass, the mass in 1 mole. So the mass in 1 mole. And that depends on the substance as well, so I put a question mark. So these are all dependent on the substance, and we'll work and do our conversions based on this, okay? But let's practice some more molar mass calculations, and also let's practice being able to break compounds down into the parts, whether it is atoms or ions, okay? So we're breaking them down. So the first thing you want to do is calculate the molar mass of each of these substances. For covalent compounds, count how many moles of atoms in 1 mole of each, and then for ionic, count how many moles of ions in 1 mole of each. So, but if it's an element, you don't have to count. You can't break it down any further. So the molar mass of copper, look on the periodic table, and you see that it's 63.55 grams per mole. And so there is really no breaking down this substance any further because it's a pure element. We go to oxygen, and there's 2 oxygens because there's a 2 subscript here. Each oxygen is 16.00 grams, so the molar mass is 32.00 grams per 1 mole. And so how do we break this down? We see 2 moles actually of oxygen. So oxygen atoms. So we're breaking it down into atoms. Sodium chloride, looking at the periodic table, calculating the molar mass. Sodium's mass is 22.99 grams. Chlorine is 35.45. Add them together, I get 58.44 grams per 1 mole. And if I have a mole of sodium chloride, which is ionic, it's going to break down into 1 mole of sodium ions and then 1 mole of chloride ions. Work through the rest of the problems and check your answers against my key. Please work through this. If it's any way to turn a new leaf this year and in this class, it is to learn to be this independent thinker and independent learner. By the way, I should have worked through this problem, so I will show you the answer, the sugar, the molar mass of sugar. I'll work it out right now. Each carbon's molar mass is 12.01, and there's 6 of them in sugar. Each hydrogen is 1.01, there's 12 of them. And then each oxygen is 16.00, and there's 6 of them. So multiply them and then add them up, and you should get 180.18 as far as the molar mass is. And I will break it down for each of these substances using my calculator that I have in front of me so that you can see how the masses add up together. So this is 72.06. This is 12.12. And I am going to add them all up later. But I have to multiply them first. So this is 96. So upon adding them all together, hopefully you see your masses to add up to 180.18. Check your answers with the rest of the key here. And make sure if you have any questions, you are going to EL time to answer these questions. Dimensional analysis is a very important technique when we're doing mole conversions. And so let's do some simple conversion with simple problems that we have that we encounter out there in the world. And one of them is converting hours to seconds. Now some of you can do this in your head pretty easily, but I'm going to show you with dimensional analysis how to set this up. The first thing you want to do is set up what is called a conversion factor. And the conversion factor, to go from hours, I first need to break it down to minutes. So this is my conversion factor. My next conversion factor is going from minutes to seconds. Now, when I do my conversion, all I'm doing is ratioing. That's all this is. Dimensional analysis is doing a long ratioed problem, and you're constantly ratioing each time you go from one conversion factor to the next without having to do a bunch of proportions one by one. You're just doing it in a single problem like you see here. So the first thing you do is you set up your given. Here's your given. Now the units that you want to set up is always going to cross cancel. So the word hour right here is going to cross cancel with this hour. And then you put the unit you want to try to get to on top. Now notice that this is a true statement. 60 minutes, there are 60 minutes in 1 hour. And that's why this converter is a correct converter. Even positioning. The hours cancel out. Now you're left with minutes at this point. Now you want to try to cancel out your minutes, so you want minutes on the bottom and seconds on the top. And when you do that, you're able to convert between your units. And then of course you're left with seconds in the end. And that's what you want to do. You want to convert your hours, 48.0 hours to seconds. And so you're going to multiply it out and do your dimensional analysis. I'm going to cross cancel the units to show you how the units work out to the final unit you want, which is seconds in the end. And all you have to do from here on out is take your calculator and multiply the numerators and then divide it by the denominator, which is pretty easy. It's 1. But always multiply the numerator, multiply the denominator, and then divide them both. And so here's your conversion. So these two are equivalent. 48.0 hours is equivalent to 173,000 seconds. You will learn to do this in atoms and molecules, or in terms of chemistry in mole conversions. So you're converting between moles to atoms. Now, what are your converters? Your converters are in the previous page. We talked about a mole equaling 6.022 times 10 to the 23rd molecules of water. And we really do have to keep track of the labeling because they cross cancel, and the labeling will help to guide us through how to solve the problem. So that's why knowing that water is covalent and knowing that it's a molecule as its represented particle is very important. So the first thing you want to do is set up your given. Start off with given. You know that moles goes on the bottom to cross cancel. You know that you want to convert your moles to smaller particles called molecules of water. And then you want to convert your molecules into atoms. So you really want to break the molecule down into 3 separate atoms because there's 2 hydrogens and 1 oxygen. That's total 3. 2 hydrogens plus 1 oxygen gives you 3. So when you're converting, you're just multiplying or setting up the mole units to cross cancel. You're also setting up the molecule unit to cross cancel, leaving you with atoms. And that's what's guiding you to solve. It's the unit, the dimension, which helps you to solve. And that's why I'm going to cross cancel the units so you can see your final unit that you want in the end, which is atoms. And multiply the numerators divided by the denominator. That will give you your final mathematical quantitative equivalent. So the equivalence of 48.0 moles of water is 8.67 times 10 to the 25th atoms. They're equivalent. That's how many atoms there are in that many moles of water. There should be a large number, and this makes sense. There's that many small particles of atoms. All right, moving on, conversions. So molar mass is a really important conversion so that you can get from grams to moles, and it allows you to do something called stoichiometry. We'll revisit this later on, but this is a very important chart for you to be able to see the big picture of what stoichiometry is, okay? All right, let's do some more conversions. Now we're going to do it with mass, okay? And so be prepared with a calculator to get some calculations in. We said that 1 mole of anything, any substance, has a certain number of mass. We don't know what that mass is, and that's why we're going to put a question mark, because it's going to differ for every substance. So it's going to vary for every substance. We're about to do what is called a mole to gram conversion, okay? So let's start off. It says, what is the mass in grams of this many moles of oxygen? So we're going to start off with our mass of oxygen, which is our given, 2.0 or moles of oxygen. And this is O2. And we want to convert this to mass using dimensional analysis. So we want to change the mole units of oxygen to gram units of oxygen. And there is a way to convert it. We know there's a way to convert it. We look at what is called the molar mass. And molar mass is found off of the periodic table. So it varies, and we're going to need to look at the periodic table to find that mass, depending on that substance. The substance is oxygen, so we know that in 1 mole of oxygen, there's 32.0 grams, because each oxygen is 16 grams on the periodic table. 2 of them is going to be 32. This will then give us the unit we want, which is the mass of oxygen. And so multiplying these two numbers, I get a value on my calculator of 80.0 grams of oxygen. I want you to pause and work through example 10. Okay, unpause. And you should see in number 10, you're always checking out the units and you're trying to cancel the unit you want so you can get the unit you desire. And the molar mass of of copper was found on the periodic table, it's 63.55 grams per mole. Alright, now we're going to reverse it. In other words, now we're going to go from gram to moles, as you see here. We're going gram to moles conversion. So here we have 102.7 grams of hydrochloric acid, and we're going to convert it to moles. So 1 mole of hydrochloric acid has 36.46 grams of hydrochloric acid. And I found that by looking at the periodic table. This is the molar mass of hydrochloric acid right here. 1 hydrogen is 1.01, 1 chloride is 35.45, and that's why it's 36.46 when you add them together. You divide those numbers, so you're really taking this number and dividing it. If it's hard for you to see this, you can put a 1 on the bottom. So you're really just multiplying the numerator, multiplying the denominator, and then dividing the two numbers together. And when you divide those two numbers, you get 2.817 moles of hydrochloric acid. Pause the video and work through example 12 by yourself. Of course, the answer is located right here as well. Okay? Unpause. When you see this, you want to, again, always cross-cancel your units so that you know that you're ending up with the correct unit. Now we go to gram to mole conversions backwards and forward. So here we're going to start off with 2.25 moles of iron 2 carbonate. And I want to write down the correct formula because my molar mass is going to bear on that very formula. So iron has a 2+ charge. Just a little review here. Carbonate is CO3 2-, so that's why it's FeCO3. Even though it's written here, you do want to practice your formulas. Alright, moles goes on the bottom of iron 2 carbonate. Mass goes on the top. In 1 mole, there is a mass of, and I'm going to have to calculate this because you're not given it so easily. Iron is 55.85, and then carbon is 12.01. Each oxygen is 16 times 3 gives you, I got 115.86. So mathematically, we're just multiplying those two values. Moles cancels out, and I get 261 grams of iron 2 carbonate. Notice my sig figs are consistent. I have 3 sig figs here, and so my answer has 3 sig figs. I'm always going to be consistent with my sig figs. Alright, pause and work through example 14, please, on your own. And check your answers, making sure you cross-cancel your units always. Grams cancels out, leaving us with moles. Alright, this next set of conversion is using Avogadro's number. So you're using this converter right here. A mole of anything equals 6.022 times 10 to the 23rd representative particles. Of course, your representative particles will vary depending on what type of substance you're looking at. It could be atoms, could be molecules, and then it could be formula units, depending on the substance. First one we're going to do is a conversion between atoms to moles. So let's start off with, if I have 3.0 times 10 to the 23rd atoms, and I want to label everything, of silver, and I want it to be converted to moles. So I know that atoms has to be in the bottom of silver so that I can convert it to moles of silver. And I know 1 mole of silver has 6.022 times 10 to the 23rd atoms. And so when I cancel this out, I'm left with moles, which is the unit I want. So you're dividing these two numbers. Now recall, when it comes to times 10, you use this E function on your calculator. So this part right here represents your EE, okay? So you use that E button and calculate it using the E button. Again, EE to the 23rd. So when you're typing this number in, you're typing as 3.01, press the E button, and then 23 divided by 6.022, press the EE button, and then put 23 as the exponent, and then you'll get your final answer, which is, in the end, 0.500 moles of silver. Oops, sorry, I put 0.55. So 00 of moles of silver. All right, now we're going to moles to atoms. You work through this and you set it up by taking the moles. The mole unit is on the bottom. 1 mole of a nickel has this many atoms of nickel. And so you just convert it and then divide, cross-canceling your units that are common. And then you multiply those numbers out and you get your answer. We're jumping into mixed problems. Just to quickly review, these are your 3 converters. Either it's a mole of a substance equals 6.022 times 10 to the 23rd representative particles, depending on what you're representing. A molecule of a substance or a formula unit can be broken down into atoms or ions, depending on what substance it is, ionic or covalent or ionic. A mole of a substance has a certain mass, and of course we know that that certain mass depends on the substance, so that's why there's a question mark. And the molar mass is found by the looking at the periodic table. So we know molar mass is just referring to the periodic table. So these are all mixed problems as we go into. So you're going to see nothing that is contrite or like set up for you. You just have to figure out which converter to use among these as you go through each problem. So I start off with my given. This is actually the most helpful starting point, is looking at the given and the units for the given. I know I need to get out of moles, and I need to get 2 representative particles. Why? Because I need to get to the atoms inside these. So I have to count how many atoms or molecules there are in this substance first. So the first step is to say a mole of CH4 has 6.022 times 10 to the 23rd molecules. How did I know to use the word molecules? Well, because it's a covalent compound, and I know that is how many molecules are in a mole of methane. So CH4. Now I'm going to convert the molecule of CH4 into atoms of CH4. So in a mole, or in a molecule of CH4, just look at this molecule. How many atoms do you see here? It looks like you see 5. 4 hydrogens and 1 carbon gives you a total of 5 atoms. So 5 total atoms. Okay. So multiply these out, cross cancel the units, not the numbers, unless they're common factors. But multiply these numbers and you should get your final answer, which is up here, 6.0 times 10 to the 24th atoms. Moving right along to example 18. These problems are pretty easy as long as you know your converters and you follow the understanding of what they mean, these units are and what they mean. So here you have copper, and notice how the word atoms appears for copper. It's the appropriate word for it. So here are the copper atoms, and I want to convert that to mass. So I know I'm going to first convert my I'm trying to get to this mass unit, but I need to get in moles. How do I get from, and I have atoms, so I need to go to moles first and then go from moles to grams. So I've got a map of what I'm going to do here. Again, I'm going to try to first convert the atoms and I know that 6.022 times 10 to the 23rd atoms of copper are in 1 mole of copper. And then I'm going to take that mole unit and cross-cancel that. So mole of copper has a mass of 63.55 grams. This is based on the periodic table, so I'm using the molar mass. Cross-cancel your units and you're left with your grams of copper. How many grams? 1.27 times 10 to the negative 14th grams of copper. In this section, we're actually doing some more conversions. It's varied, mixed, of course. Moving to 19, I'm starting off with 4 grams of sulfur atoms, and I'm going to need to convert it to atoms, so number of particles. I first need to convert my grams of sulfur, which is 32.07 grams of sulfur in 1 mole of sulfur. And then I need to take my moles of sulfur and convert it to atoms. And they're 6.022 times 10 to the 23rd atoms of sulfur in a mole of sulfur. Cross-canceling those units out, I'm left with my atoms of sulfur, which is what I want. And so I multiply and divide those numbers, and I should get my answer in the end, which is 7.51 times 10 to the 23rd atoms of sulfur. Now I'm going to try to find the number of chloride ions, which means I need to get to the particles. I need to get to how many ions, which means I need to get to moles, because I need to use Avogadro's number to get to the number of particles. So I start off with 72 grams of magnesium chloride, and I'm going to need the molar mass. And I know that each mole of chlorine is 35.45. Times that by 2, because there's 2 of them right here, and then add magnesium, which is 24.31 mass in terms of its mass. So adding them all together, you get the molar mass of 95.21 for every 1 mole of magnesium chloride. Now you want chloride ions, which are really small. They're the smallest unit of an ionic compound. So you really do need to convert your moles of magnesium chloride into formula units first. And we know that there's 6.022 times 10 to the 23rd formula units. I'm going to abbreviate, of magnesium chloride. Now, I need to also take that formula unit, and I can break that formula unit down into the ions. And how many chloride ions in each formula unit of magnesium chloride is there's 2. Notice the 2 right here. There's 2 chloride ions. So I'm going to say 2 Cl ions. And multiply and divide, cross-cancel your units. You're noticing units to be cross-canceled, and they cross-cancel nicely to give you your chloride ions. And your answer in the end is 9.1 times 10 to the 23rd. Okay, lots of calculations. Now these calculations lead to what is called the calculations for percent composition, empirical formula, and molecular formulas. So let's talk about what percentages are. If I were to ask you to calculate percent by gender, percent composition by gender in a population, and the population we're looking at is our classroom. Say we have 30 students in our class. Of the 30 students, there are, let's make it easy. Actually, we're going to make it a little harder. 10 boys. Actually, that's pretty easy. 10 boys. What is the percent of boys in the class versus the percent of girls? We've always learned that percentages are part over whole times 100, ratio to 100, okay? And so boys, as far as boys is concerned, we're going to do 10 boys out of 30 total students, okay? And when you do that, and you do your part over whole, you get 33.3%. Which means the girls is pretty easy. You just take 100 minus that, because it's a percent. 100% minus the other part, which is 33.3%, and you should get 66.7%. And this is the girls. So percentages are easy. It's very basic. It's part over whole. And that's precisely in chemistry what it is. You take the part, which is the mass of the element you're looking at, and then you take the divide it by the whole, which is the molar mass of the whole compound, and you times it by 100. So when you try to find the mass percent of each element in carbon dioxide, and what are the elements that make up carbon dioxide? There's carbon and there's oxygen. So you're doing the percent of carbon in carbon dioxide as well as the percent of oxygen in carbon dioxide. Now the total mass of carbon dioxide, molar mass of it, is really found on the periodic table. There's 1 mole. 1 mole of carbon has a mass of 12.01. 2 oxygens is 32. You add them together, you get 44.01. In carbon dioxide, there's only 1 mole of carbon, so that's 12.01 grams. So this is mass percent. This is percent by mass. Notice the gram units right here. Times it by 100, this is the percent of carbon in carbon dioxide. Now you could take the difference from 100 and get the percent of oxygen, but we're literally going to calculate it from this equation. So the mass of oxygen, since there's 2 of them, that's 16 for each one, but 2 of them is 32. Divided by the total, and then times it by 100, and that will give you the mass, or the percent of oxygen in carbon dioxide. All right. How is this going to be relevant? Well, it allows us to, this whole percent idea allows us to calculate what is called empirical and molecular formulas. The molecular formula shows exactly how many moles of each atom is present in a compound. They're usually multiples of the empirical formula. What is the empirical formula? It shows the lowest whole number ratio of that formula. So let's go ahead and take a look at examples of this in this chart. I really wanted you to look at it without the answer, but since I have the answer, it's okay. Now, notice how the empirical mass right here is the molar mass of the empirical formula. It's 17.01. And compared to the molecular mass, it's twice. So you know that whatever the empirical formula is, the molecular formula is twice. And so that's why you see doubling of each of the moles of each of the given element, okay? Likewise, let's go over here. Now, if it's hard to see, if it's hard for you to see the relationship, this is twice. This is quite easy to see. Oh, there is an error here. It's supposed to be twice. So if it's twice, that means the formula is going to be twice. So the error is 2 and 4 here. Okay. Now you're going to go work backwards. If you're given a formula like this and you want to find the empirical formula, all you do is reduce this 4 to 12 ratio. Reduced, you get a 1 to 4 ratio. And of course, that means if you're dividing the formula by 4, you're also going to divide the molar mass by 4. And so by dividing 55.32 by 4, you get 13.82. Now, sometimes the molecular formula is exactly the empirical formula, and how you know that is if the molecular formula's mass equals the empirical mass. So molecular mass and the empirical mass are equivalent. That means the formula is the same. Keep on working through it and check your answers as you go through each one of these, okay? Okay, so in example 22, it says the molecular mass of diborane with empirical formula of BH3 is 27.67 grams per mole. What is the molecular formula? And so we want to calculate the empirical formula of BH3, which is, if you notice, BH3 is in its lowest whole number ratio. It's a 1-to-3 ratio. You can't reduce it into any lower of a whole number ratio than 1-to-3. So the first thing you want to do is calculate the molar mass of BH3. And B, the mass of B, I'm looking for it, is 10.81 on the periodic table. And the mass of 3 hydrogens is 3.03. And so the molar mass is 13.84. Now, once again, when you can't recognize what multiple this number is to this number, you just divide them. Divide the bigger number, which is 27.67, divided by the smaller number, 13.84. And when you divide those two numbers, you'll see that it's a multiplier of 2. So you're going to twice that of BH3, which is B2H6. So that is the molecular formula that we're looking for. In example 23, what is the molecular formula of a substance whose empirical formula is BH3 and has a molar mass of 41.52? Hopefully you'll pause and work through this problem, working it through the same exact way as you did in example 22, but with, of course, a different molecular mass. And when you unpause, you'll see my answer key. So here is my answer key. Now we're going to go backwards. We're calculating the empirical formula given the percent composition. With problems like this, because percentages are based off of 100, it's nice to assume you have 100 grams of this whole compound that has boron and hydrogen in it. So we start off by making an assumption, and the assumption is we have 100 grams of this compound, which we don't know is what its formula is, so we call it BXHY. We do know that the X represents the moles of boron, the Y represents the moles of hydrogen. And so we're going to calculate. We're going to take the mass, knowing the percent by mass of each of these elements. We're going to take that percentage straight out and get the mass from it. So if 78.1% is boron, 78.1 of 100 grams of BH or BXHY is boron, we just take that percent right off of that, and that would be 78.1 grams of boron. Now we want to convert it to moles because that X represents the moles of boron. So converting our grams to moles, we do a simple molar mass conversion, and we get 7.22 moles of boron. We do the same thing for hydrogen, 21.9 grams of hydrogen divided by the molar mass, you'll get the moles of hydrogen. Now if you substitute it into the formula, you'll get something that doesn't look familiar to you. Usually these numbers are whole numbers. So to get them into whole numbers, you divide it by the lowest molar value. In this case, which one is a lower value? You're right if you said 7.22. So you divide it by 7.22. You will certainly then get whole numbers. It's a 1-to-3 whole number ratio. You don't have to write the 1 there, so you can just call it BH3. And that is truly the formula of diborane. Okay, I'd like you to work through this next example, example 24. Make sure you work through it and get your final answer. certainly try to assume 100 grams because that's what percentages are based off of. You're ratioing it to 100, so why not assume you have 100 grams of the compound? And then do all your conversions as necessary, and then um, you should pause and work through this yourself. But once you unpause, you'll finally get the final answer. So you know that this is 3.33 hydrogen, which is 6.63, and then oxygen, which is 3.33. Divide all of them by the lowest molar value, which is 3.33. Get C1H2O1. And that is the empirical formula. Work through example 25 as well. And when you unpause, you'll see the final work and answer. Alright, so here's the answer, and hopefully you can double check your work, run through the problem, and check. I do want to cross cancel my units where I see cross canceling needed. I did forget to do it in the previous problems, and so I'm going to go back and just cross cancel units and see the cross canceling, how it yields the dimension or the units I would like in the end. Okay. Work through example 26, very much similar. You're trying to find the empirical formula and molecular formula in this case of isooctane. Once you pause it and once you unpause, you should see the answer. So you can't take a 2.24 value and round it to a whole number. So you have to find a multiplier once you get to this point in the calculation. You have to find a multiplier that will allow you to get to whole numbers. And I look at this fraction or this decimal right here. It looks like a quarter if you think about it, 0.25, close to a quarter. And so a good multiplier for this to try to get it to close enough to a whole number would be multiplying by 4. So I'm going to take this whole value and multiply by 4. And I'd have to do it for both. So 4 and 4. Upon doing it for both, I get C4H9. And so this is my empirical formula. To find my molecular formula, it's just a matter of figuring out my molecular mass and comparing it to the molar mass of my empirical formula. So I'm going to find the molar mass of my empirical formula, and it turns out to be, I'm going to multiply that, 57.13 is my empirical mass. And I need to compare it to my molecular mass. And so I'm going to divide those two numbers, 114 divided by 57. And it looks like it's a multiplier of 2. So my molecular formula is twice that of my empirical. So it's C8H18. That is my final answer. I also do have to find the percent by composition. Okay, so percent composition is simple enough. You just take your percentage of carbon is calculated by taking part over whole, 0.5040 grams of carbon over the whole. And the whole is 0.5992 grams of this compound that both has carbon and hydrogen. So you should get your percentage of 84.11% carbon. And you would also do it for the percent of hydrogen, doing the same steps. So you've got 0.09515 grams over the whole, which is 0.55 or 0.5992 grams. And when you divide those numbers and times it by 100, of course, don't forget to multiply by 100. You are trying to find a, a percentage, which is a ratio to 100. And so this answer is 15.88%. Sorry for that little bit of squeeze. So here are our answers, including our empirical. This is our molecular formula. Alright, so the question is, when would you multiply by a multiplier? Any number where there's a 0.5 decimal, you double it, because the fraction is 1/2. And to take that fraction and to turn it into a whole is to multiply by the denominator, which is 2. Multiplying by 2, you will get a whole. Likewise, when it's 0.2425, close to that, you'll multiply by 4 and you'll get whole numbers from that. If it's 0.33, you know that's a third, and so multiply by 3 and that will give you your whole number. If it's 0.66, that's 2/3. Once again, denominator is 3, so multiply by 3, you'll get whole numbers. The closest, lowest whole number. And then, of course, 0.75 is 3/4. That's a fraction, and so you multiply by the denominator. So on all of these, in order to get whole numbers, you multiply by the denominator of these fractions. So it's important to know and recognize your decimals and how to convert it to fraction form, so you know what the multiplier would be. I'd like you to work through the next problem, 27, and make sure you understand the answers right here as well. So pause and work through it yourself first, and then you can check your answer. Alright, let's get into hydrates. When it comes to hydrates, we know that hydrate means water. And so it's dealing with an ionic compound that's surrounded by water, because ionic compounds have charges. Water is polar. They attract each other in this crystal lattice structure. We're going to draw and model copper 2 sulfate pentahydrate, so 5 water molecules. And when we draw it, we're going to really be cognizant of where the charges are. So copper has a 2+ charge, sulfate has a -2 charge. We know that water likes to orient around copper such that the oxygen is going to orient towards the copper. So I'm going to draw oxygen towards the copper. And these are lone pairs, if you recall. And then around the sulfate, I'm going to put the hydrogens, because the hydrogens are partially positive, whereas the oxygen is partially negative. So those are your 5 water molecules for every 1 formula unit of copper 2 sulfate. 5 water molecules for every 1 formula unit. This is a very microscale illustration of it. So we're really looking at just 1 full unit of this. When you name these compounds with and without the polyatomic ions, or if you name these hydrates, you recall that you use your naming rules for ionic compounds with or without the polyatomic ions. And then for the hydrate part, you add the proper Greek prefix. So we're just going to refresh our memory on naming hydrates. In naming hydrates, these are the proper prefixes that you all should understand and know. This is from the past years of grade school all the way to middle and high school that you've acquired as far as prefixes. Let's go ahead and learn to name or review naming. This is peer review. So barium chloride. Barium has looking on the periodic table, has a 2+ charge. Chloride has a -1, so it's BaCl2. Dot to represent hydrate, and there's 2 because it's di and water. And then, of course, to name this, it's called barium, and I see hydroxide in it. Never modify the name of the polyatomic ion. And then we call this octahydrate. The next one is calcium nitrate. Calcium has a 2 plus charge, nitrate has a -1, and nitrate's NO3. And so I need 2 of it. And then it's tetra. Tetra is 4, and water. Stop and pause and work through the rest and check your answers with my key right there. When you have an anhydrate, an means without, and so hydrate means without water. Anhydrate is without water. So it's an ionic compound. Basically, you've driven off all the water, so you're left with an ionic compound. So for copper 2 sulfate, if you drive off all the water by heating it up, you have what is called, you have this compound, which is the ionic compound left, and that's copper 2 sulfate. So let's figure out how to do formulas of hydrates versus anhydrates. In these problems, it's very similar to how you do your previous sections on percent composition of molecular and empirical formula. It's very similar to that, but now you're dealing with just specifically a hydrate. Now, understand when it comes to hydrates, what you're looking at, what you're seeing ratio-wise is a mole ratio. So let me write the hydrate of copper 2 sulfate pentahydrate. And what the ratio is a 1 to 5 mole ratio between the copper 2 sulfate and the water. Now, this is macroscale. So macroscale means a lot of particles. A lot of particles means moles. And so it's a 1 for every 1 mole of copper 2 sulfate, there's 5 moles of water. Now you can look at it microscale, and we did illustrate last page, the previous page, copper 2 sulfate pentahydrate on a microscale, and we saw that we looked at 1 unit, formula unit of copper 2 sulfate for every 5 molecules of water. So understand that moles is macroscale, molecules and formula units are micro. So you're really looking at small particles. When we do chemistry, we tend to calculate in large amounts of the particles, and so moles is the unit of choice. In this problem, it says anhydrates lithium perchlorate was dissolved in water and recrystallized. Care was taken to isolate all the lithium perchlorate as its hydrate. The mass of the hydrate salt obtained is 7.21. What is the hydrate? So here's your anhydrate, and this is your hydrate. So if you think about this, the only difference in the mass is the difference of the mass of the water. This is with water, this is without water. So when I subtract those two values, logically, I get the mass of my water. Now I also have the mass of my anhydrate, so I need both. I need both the mass of my anhydrate as well as the mass of water to do a mole ratio between the two. And that's exactly what I'm going to do. I'm going to start off with my anhydrate, which is lithium perchlorate. And I know perchlorate, ClO4, lithium's Li, and the Li has a +1, perchlorate has a -1. So then I convert my mass into moles. So looking at my periodic table, the molar mass of lithium is 6.94. The mass of chlorine is 35.45. The mass of each oxygen is 16 times that by 4. I get a molar mass of 106.39 grams. So 1 mole of lithium perchlorate has a mass of 106.39 grams. Not done yet. Now I'm going to do a mass difference. A mass difference to figure out how much water. So when I take my hydrate, so this is my hydrate, and I deduct my anhydrate, I should get water, the amount of water that was driven off. And deducting these two numbers, I get 2.5 0.43 grams of water. And I want to convert that to moles. My molar mass is 18.02 grams. And dividing 18.02 gives me 0.135 moles of water. Now my formula looks like this. It's X and Y for the water, mole-wise. So X of lithium perchlorate, Y for water. And I want to find that formula by ratioing. And likewise, or like we did earlier, we look at these two numbers and we see that these two numbers are not really nice whole numbers. So we're going to insert. I obviously did not calculate the moles of lithium perchlorate, and I should have. Ends up being 0.0449 moles. So I'm going to substitute all these values in, and I'll do it in black so you can contrast it. 0.0449, and then the other number is 0.135. And this is lithium perchlorate, and this is water. So we see that this number is not a whole number, so we divide it by the lowest molar value. In this case, it's 0.0449. And when we do that, our coefficient ends up being a 1 coefficient. And usually that's going to be the case for your anhydride or your salt. So then, and when we divide 0.135 divided by that value of 0.0449, I get 3. So it's a 1-to-3 ratio. So for every 1 lithium perchlorate, there's 3 water molecules. That's how you do that. Go ahead and try out example number 29. Again, try to assume you have 100 grams of the hydrate, and that should help you to be able to maneuver through the problem pretty nicely. Pause, and then when you unpause, you will then see the final answer and the work for it. So here's the answer, and you'll notice that all these numbers tend to leave you with this whole number ratio when you work through it correctly. So inevitably you're going to get whole number ratios, whether it's a hydrate or just a formula of any compound. So another way we can go about finding the formula of an unknown compound is through a technique called combustion analysis. Combustion analysis is literally you're taking an unknown compound you don't know the formula for, and then you put it in a combustion chamber that looks like this. When you combust it by burning that substance in oxygen, you then see that carbon dioxide forms water vapor forms as well as carbon dioxide. And you have an absorber that will retain all of those molecules of carbon dioxide from that combustion reaction as well as water vapor. In doing so, you know that all the samples, all the hydrogen that's in water is actually coming from the actual original sample. So all the hydrogen comes from the original hydrogen in the sample, unknown sample. Likewise, all the carbon comes and is conserved in the original carbon of the unknown sample. So everything is, the masses are conserved. Now you're going, what about the oxygen? Well, oxygen is in multiple placements, as well as the amount of oxygen that you're reacting to combust the compound is going to be oftentimes in excess. There's a lot of it. So it's hard to trace oxygen, but there's a way to trace it as long as you understand conservation of mass. And we'll talk about that when we get to those problems. But we're going to try to take the masses that are given to us of both carbon dioxide, our knowns, and figure out how many moles of carbon and hydrogen. That way we know the moles, which is your X and Y of the carbon and hydrogen. The oxygen we'll figure out by taking the difference of the masses of the hydrogen and carbon from the original mass of the compound that's given to you. So you do mass the sample when you're combusting it. And so you can get the mass, if you know the mass of hydrogen and carbon and hydrogen, you then can deduct that from the total mass of the sample, and that way you can get the mass of the oxygen. From the mass of the oxygen, you can get the moles of the oxygen. So ultimately, these X, Y, and Z's are all representing the moles of carbon, the moles of hydrogen, and the moles of oxygen. And we're trying to find those moles so that we can find the formula of this unknown sample. We'll do one problem and we'll work our way to solving using combustion analysis. So, if you read it carefully, and you always do want to take a careful read, you're given the mass of your unknown sample that has both carbon, hydrogen, and oxygen, and you're burning it in oxygen, so it's a combustion reaction. The subsequent analysis of the gaseous results yields in the following grams of carbon dioxide as well as grams of water. So you're often able to find the masses of the two products that result from the combustion reaction. Once again, the carbon is what's important and the hydrogen is what's important from each of these components. So the first thing I'm going to do is I'm going to take the 18.942 grams of carbon dioxide, and I'm going to try to get moles of carbon from that, okay? To do that is to do the molar mass. First convert it into molar mass of carbon dioxide. And then I'm going to mole ratio and break the moles of carbon dioxide into moles of carbon. And I know that 1 mole of carbon dioxide, so if I have a mole of this whole thing, I have how many moles of carbon? Just 1, because there's a 1 subscript here. So I'm going to put 1 mole of carbon. And I'm going to do the same deal here with my water. Now I'm going to do a calculation stopping here, but I'm also going to do a calculation where I want to get to the mass of carbon. So 1 mole of carbon has a mass of 12.01 grams of carbon. Now why do I want both? Because I'm going to try to find the oxygen, the mass of the oxygen. Okay, so I'm going to put the moles in black. So when I divide these, multiply and divide, so it's 18.942 divided by 44.01. I get a mole value of 0.430 moles of carbon. Now when I multiply that value times 12.01 and get the mass of carbon, I get 5.169 grams of carbon. Okay. Now I'm going to do the same thing with water. So I'm going to take 7 sorry, for some reason I got rid of that in carbon. Now I'm going to take 7.749 grams of water, and I'm going to convert it to moles. And again, I'm always noticing whether I'm cross-canceling the units that I want to cross-cancel. So I haven't shown the cross-canceling, but I will soon. So I know that 1 mole of water has 2 moles of hydrogen. And I'll show you where that 2 is coming from. The 2 is coming from the fact that 1 mole of this whole thing has 2. You see the 2 hydrogens? That's where the 2 comes from. And once again, I'm going to do an equal part right here and stop right there and do a calculation. But I'm also going to do the mass. So a mole of hydrogen has a mass of 1.01 grams of hydrogen. So calculating both, I've got 7.749. I'm going to divide it by 18.02. And then I'm also going to multiply it times 2. And I get 0.860 moles of hydrogen. And then I'm going to multiply that times it by the molar mass. That's 0.869 grams of hydrogen. And I'm going to add these 2 values together. Upon adding these 2 values together, I'm going to get the total mass from both carbon and hydrogen. So my total mass is 6.038 grams of both carbon and hydrogen. Now, what is the relevance of getting carbon and hydrogen, the mass of it? Well, if I know the total mass of the sample, which has both carbon and hydrogen and oxygen, if I know the mass that's in that total mass of both carbon and hydrogen, I can deduct that from the mass of my original sample, which has all the elements. And by deducting the carbon and hydrogen, I will get the mass of the oxygen. So, taking that very logic and following through with that logic, if I take 12.915 and subtract, and that has both carbon, hydrogen, and oxygen, I will get the mass of my oxygen. And it turns out that oxygen, when I subtract is 6.877 grams of oxygen. And now I can then convert my grams of oxygen into moles of oxygen. And my value, I'll make it in black so I can be consistent. Is 0.430 moles of oxygen. So I have all the moles of each of my components, and I just need to put it into the formula. And my formula, and I'm going to work my way up here so I have room. So my formula is carbon 0.430, hydrogen 0.860, and then oxygen 0.430. So I have my moles, and I know I'm going to divide it by the lowest molar value. And when I do that, I get C1H2O1. So this is my empirical formula. I did want to make sure I cross-cancel all the units that deserve cross-canceling. That's how I'm tracking my dimensional analysis, is through the units and knowing my units are correct. I would like you to work through example 31 by yourself and then pause right now so that you can do that. You will see the answer after you unpause. Alright, go ahead and check example 31's key and the work that you see right there. Let's move on to stoichiometry after this. Stoichiometry is really broken down into its Latin roots here, or its Latin roots. Stoich means element, and ometry is measurement. So you're really measuring the amounts of the elements, and you're making sure that the mass relationship between reactants and products is conserved in the balanced chemical reaction. And this methodology, this skill is used to predict how much product can be produced given certain amounts of reactants using what is called a mole ratio. So you can actually call it mole ratio or molar ratio. I oftentimes call it mole ratio. Mole ratio is the proportional relationship, which is the conversion factor between reactants and products on the balanced equation. Be sure, once again, to always label your units and your substances. So I'm going to add that, and substances. And then cross-cancel units, because you're actually going to be using dimensional analysis. So you're really still going to use dimensional analysis, but we are first going to conceptually understand stoichiometry through doing it in our head and proportioning it out in your head. So let's simplify this example. This is how we're going to really conceptualize it. We're looking at a simple example. One car needs 4 tires to make one full car. So one body needs 4 tires to make one full car. If I had 8 bodies, what would I need? I need 4 times that amount, which is 32. 4 times 8 is 32 tires to make 8 cars. So this is the stoichiometric. You can look at this in terms of stoichiometry in a balance equation. So we're going to look at an actual balance equation. In this reaction that you see, where you have oxygen reacting with hydrogen to form water vapor, the mole ratio is for every 1 mole of oxygen reacts 2 moles of hydrogen to form 2 moles of water vapor. Now that's the macro scale. So moles is really a lot of particles. Now we go to microscale. You can actually interpret it as 1 molecule of oxygen reacts with 2 molecules of hydrogen to form 2 molecules of water vapor. So you can interpret it macroscopically in moles or microscopically in molecules, atoms, or formula units, depending on the substance. But the key is to understand these proportions. This is a 1 to 2 to 2 ratio. So you can look at it and interpret it like this. You need twice as much hydrogen as you have oxygen to form twice as much water vapor. So there's 2 different levels of interpretations here. Now, if you do it microscopically on a microscale, and you're reacting here 1 molecule of oxygen to 2 molecules of hydrogen, what you would expect to form is 2 molecules of water vapor. And so I'm going to draw 2 water vapor molecules to hold up for what you would expect to form. Now, what if instead of 2 water molecules, now we're going to throw this scenario off a little bit away from still the actual ratio that you see, the mole ratio you see, but we're going to still proportion it out to make sure that the ratio is in fact adhered to. Okay? So let's take a look at what we're looking at in this next microscale. So on a microscale level, it asks how many oxygen molecules would react with what's given to us. And what's given to us is a count of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 hydrogen molecules here. So how much oxygen would react with that 12? Well, half. We know half because it's a 2-to-1 ratio here. And so what I would draw to represent that microscale illustration is 6 oxygen molecules. So, and they're diatomic. So there's your 6 oxygen molecules. And it says next question is how much water would form from the complete reaction of the hydrogen gas molecules. And we know here that if you have 12, you know that the same amount of water is going to form because it's a 2-to-2 ratio here. So I'm going to draw 12 water molecules. And be patient with me. I'll pause it and draw it, and then you'll be able to see the answer in the end. So notice how the ratio of oxygen to hydrogen to water vapor is in fact, it's a 6 molecule, so MLC is going to be my shorthand for molecule, and 12 molecule, MLC, to 12 molecule. Notice how this ratio really aligns with the stoichiometric mole ratio. It's a 1 to 2 to 2. You reduce a 6 to 12 to 12, it reduces down to a 1 to 2 to 2. So that ratio really has to adhere very well to the balance equation. All right, let's move on to the next. I would like for you to try out this next particulate microscale level drawing. It's asking you in this next problem how many moles or how many oxygen and hydrogen molecules would be required to form the given amount of water. And how much water that you see here is 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 water molecules. I'm going to write that down, 8 water molecules. And you've got to fit that ratio, so think about how many molecules you would draw. Pause the video and go ahead and draw the the oxygen molecules as well as the hydrogen molecules. When you unpause, you'll see the answer. And so again, notice how you end up with 8 molecules of hydrogen and 4 molecules of oxygen. Notice the ratio. It's a 4 to 8 to 8 reduced down to a 1 to 2 to 2. So you'll notice that all the ratios of reactants and products perfectly align with the stoichiometric mole ratio of the balance equation, as you see above here. So it's very important that you understand that this is basically what you're doing when you're doing stoichiometry. You're just fitting into the ratio of the balance equation. And that ratio is really, the balance equation is your recipe. You're just following the recipe for how the reactants react to form the products. So let's go ahead and look at example 32. In example 32, you've got a balanced equation. It's a 1 to 2 to 2 mole ratio. So you're given here in the first problem 2 moles. And I know this is going to be twice. So I know that this is going to be 4 moles. And of course these two ratios are the same, so it's 4 moles here as well. So notice how this 1 to 2 to 2 ratio, given 2 moles of oxygen, you're still going to fit the 1 to 2 to 2 ratio as well. And that's all we're doing. Stoichiometry is about ratioing and proportioning. So here we have 8 moles given to us of hydrogen. We know that it's going to be the same for water vapor, and so it's 8 moles. And then half that amount is going to be oxygen that reacts. So 4 moles of oxygen. Again, ratioing it, noticing 1 to 2 to 2. This reduces down to a 1 to 2 to 2 ratio as well. So they all will fit the mold of the 1 to 2 to 2 ratio between the reactants and products. Let's get down to, go ahead and practice the rest. Pause the video and practice the rest. But after you unpause the video, you'll see going into G and H, you'll see that you have to do a gram to mole conversion of these substances. And that's just simply taking your grams and converting it to moles. And to do that is just to use the molar mass. So this is going to yield 3.00 moles of water vapor. So that's all I'm doing for each of these in order to convert my gram to moles. And you cannot ratio grams. This is not a gram ratio. This is a mole ratio. Work through the rest of this problem and make sure you always see a 1 to 2 to 2 ratio. Let's go down to example 33. Now, when you now know what Stoich is. Stoich is just ratioing based on the balance equation. What we're going to do is we're going to use dimensional analysis to show for how we're ratioing. So let me show you how to do that. Starting off with 33A, it says how many moles of hydrogen gas are needed to react with 3 moles of oxygen gas. So you start with your given, and you're using, again, dimensional analysis to do this. And you're starting off with 3 moles of oxygen gas. What you want to do is ratio moles of hydrogen on top is what you need. Moles of oxygen is what you're trying to cross cancel. Notice the units to cross cancel are the same here. So you can get to the units you desire, which is moles of hydrogen. Now, what's the ratio between moles of hydrogen to oxygen? Well, it's exactly from the balance equation. Here's oxygen, here's hydrogen. So 2 moles of hydrogen to every 1 mole of oxygen. And that's precisely what I'll put. 2 moles of hydrogen to every 1 mole of oxygen. And when you divide these or multiply these two, you'll get 6.0. Notice the sig figs. There are 2 sig figs here. Your answer should be 2 sig figs as well. So your answer is 6.0 moles of hydrogen. Notice the cross canceling of your units leading to the final units you desire. Let's go ahead and look at the next problem. In the next problem, it says how many moles of hydrogen atoms can react with 3 moles of oxygen. So now you're digging into the hydrogen molecule so you can figure out how many moles of hydrogen atom. So we're going to take a couple of steps. We're going to need to take an extra step with this problem. You start off with 3 moles of oxygen, which is your given. You have to get 2 moles of hydrogen. So you're doing the same setup. 2 moles of hydrogen to every 1 mole of oxygen. Now that's hydrogen molecule. Now we have to get to atoms of hydrogen. So 1 mole of hydrogen molecule, there's 2 moles of hydrogen atoms. And so that is your extra conversion there, leading to what you desire, which is moles of hydrogen atoms. Multiplying all this, you get 12 moles of hydrogen. I'm always labeling my substances as well as my units and substance. So I can see the cross-canceling and the maneuvering through this problem as I solve it. So pause the video and work through the rest of the problems and unpause to check your answers. The answer key is obviously right here, as well as the work. The work is below that. Let's jump down to E. In E, you're asked to draw the particulate diagram for 4 hydrogens for where the reaction is such that 4 moles of hydrogen is proportional to 4 molecules. In other words, instead of drawing 4 moles of hydrogen, which, by the way, is pretty large, it's like 2.4 times 10 to the 24 molecules of hydrogen, which is a lot of particles to draw. Too many for me to be able to draw in one lifetime. I am going to instead treat the 4 moles as 4 molecules because I'm going to represent the microscale. I'm scaling it to the smaller particulate level drawing. Okay, and in doing so, 4 moles would represent 4 molecules. And I'm going to draw hydrogen as it shows right here, since it's black and it's diatomic. So here's hydrogen, here's another hydrogen, here's another one. So I'm drawing 4 of them as directed to do. So here's my 4 hydrogens, 4 molecules of hydrogen. Now I need to draw oxygen. Now when I draw oxygen, I'm looking at drawing something proportional to that. So I'm going to figure out how much oxygen there would be from that proportion. And I know that the amount of hydrogen, the amount of oxygen is going to be half of that based on the number of hydrogens. So there's 4 of these hydrogens, so half of that would be 2. So I shall draw 2 molecules of oxygen. Go ahead and work through example 34 on your own, and then check with the work that I have and the answer key that is given to you. So we're going to move on to mass problems. It says no calculators, so these numbers are actually pretty straightforward and simple for you to be able to do your calculations. It doesn't mean you won't be allowed. I'll allow calculators on the tests, or on quizzes and tests. But I just wanted to make sure that you're calculating with you're thinking through the ratios and the proportions rather than being consumed with the numerical values. So here we have the first problem saying aluminum reacts with chlorine gas to form aluminum chloride. The reaction that you see would be this right here. Remember that chlorine is a diatomic molecule, and aluminum and chlorine are going to combine to form this ionic compound that's neutral, which is aluminum chloride. The ratio when you balance the whole equation is a 2 to 3 to 2 mole ratio. So now let's go ahead and look at the first example. It's a little bit colliding with the information, which is the molar mass given to us. It's going to be fine though. Okay, so the first thing you want to set up is find your given, which is 5.4 grams of aluminum, and it's asking you for the grams of aluminum chloride. So we have to convert between aluminum and aluminum chloride, and the conversion requires that you first convert your grams to moles of aluminum. So we can do a mole to mole ratio here. And in doing that, you use the molar mass of aluminum. So I'm taking grams down here, moles of aluminum on top, and then I'm going to do a mole ratio between aluminum and aluminum chloride. And in doing that, it's a 2 to 2 ratio, which reduces down to a 1 to 1. So I'm going to simplify my math a little bit and reduce where I can reduce. So aluminum to aluminum chloride is a 2 to 2 ratio, but reduced down to 1 to 1. And then I'm going to take that moles of aluminum chloride and convert it to grams of aluminum chloride. And so I need the molar mass of aluminum chloride, which is provided for me up here in this box here. And that will then give me the final unit that I desire, as long as I show the cross-canceling of my units. And notice how everything labeled is also cross-canceled, the substances, leaving me with the grams of aluminum chloride, which is what I desire. Pause the video and work through the next problems B and C on your own. Check your answers as well as the work that you see. When you unpause, you will see me cross-canceling all the appropriate units, leading to the final unit that I desire in the end. Alright, let's go to number 36. In number 36, you're doing a mass a mass to mole problem. So it really is pretty much one of these problems, but cut down to one of the steps where you're not doing a mass conversion using molar mass. So here you have another reaction. It's aluminum oxide, which is right here, formula-wise, decomposes into aluminum and oxygen. Once again, oxygen is diatomic, and then you balance the equation. It's a 2 to 4 to 3 ratio. The first question is, what is the mole ratio between aluminum and aluminum oxide? So here's aluminum. Here's aluminum oxide. It's a 4 to 2 ratio in that order, in the order that you see right there. Now, 4 to 2 ratio can be reduced down to a 2 to 1 ratio. What's the mole ratio of oxygen to aluminum oxide? Oxygen's right here, 3 to every 2. So it's 3 to 2 ratio here. It's making sure you understand mole ratio and the relationship of mole ratios. All right, work through C and D and making sure you check your answers as you go through this. Practice is what you need to do, and it has to be independent. So you have the answer right there. So please make sure you're working through it on your own once again, and then checking the work afterwards. So I'm going to cross cancel my units where I see can be cross canceled. All right, so now you're doing particulate drawings. So now 1 mole of aluminum is proportional to 1 atom of aluminum. So you're taking the macro scale and turning it into a microscale diagram. And aluminum is going to be in red, and it looks like we're looking at part C, which means you have 2 moles of aluminum. And why I say that is because if you have 204, 4 moles of aluminum is what you're looking at. I'm going to, this drawing is a little bit obscure, a little bit in error. And why it's in error is because the arrow is supposed to be this way. And I'll edit this drawing on your set of notes. And then this is a plus. So the arrow goes this way, and then the plus. So what we're looking at is aluminum, which is there's 4 moles of aluminum. So right here in this container, 1, 2, it's an atom, so it's not diatomic, it's just a singular atom. So if you have 4 moles right here of aluminum, you know that the amount of oxygen, which is diatomic, is going to be 3 of that. So we're looking at the ratio of the equation. So for every 4 moles of aluminum, or 4 molecules, 4 atoms of aluminum, because it's a single element, you're going to see 4 molecules of oxygen, or 3 molecules of oxygen, my apologies, because it's a 4 to 3 ratio between the two. And then the amount of aluminum oxide is going to be 2 of them. Now, aluminum oxide is a solid, and I'm going to draw each unit of aluminum oxide let me start off with the reds, okay? 2 aluminum oxides, and it's going to have a crystal lattice structure, so watch me do this so you can see how I would draw aluminum oxide. And so here's I'll make my aluminums a little larger. Because my legend looks to make it look larger. Okay, and then there's 2 aluminum oxides, or aluminum in aluminum oxide. And then I'm going to draw oxygen. So there's 3 oxygens. And notice the crystal lattice, the pattern, this crystal lattice structure. So this is aluminum oxide right here. And I'm going to draw two of these. So I don't think I should have drawn aluminum or oxygen so large. There you go. So there's your 2 moles or 2 formula units of aluminum oxide because it's ionic. So you've got 2 formula units of aluminum oxide to every 4 atoms of aluminum to every 3 molecules of oxygen. Now notice the ratio is fitting to the ratio of the balance equation. Let's look at combination problems. Example 37. In example 37, class, what you want to do is make sure you balance this equation, starting off with the iron looks balanced between the reactants and products. This tin also looks balanced. The nitrate ion doesn't. There's 4 here, and then there's 3 here. So what I like to do when there's a 4 to 3 here, and I need to balance those two, is find the common multiple between the two, and that's 12. So I know when I balance this equation, it's going to be 3 here and 4 here to make 12 nitrates, which I can independently balance out the iron, so I need 4 here and 3. So the ratio is a 4 to 3 to 4 to 3 ratio, mole ratio. I'm going to now calculate based on what the problem that's presented to me. So it says right here that I want grams of tin given grams of iron. And so I'm going to start off with my given, which is grams of iron, 112. It looks like I have the work here. 112 grams of iron. And then I'm going to convert that grams to moles of iron. And then I'm going to do my mole ratio between iron and tin, which is 4 for every 4 irons. There's 3 moles of tin, so it's a mole to mole ratio. And then I'm going to convert my moles of tin to grams of tin. And so that's my molar mass of tin found on the periodic table. So just a quick summary of how this all works. I do want to make sure you're seeing that all you're doing is using these converters. So this is the molar mass of iron. This is the mole ratio between tin and iron. And then this last one is the molar mass of tin. So you're using just various converters. These are all converters that allow you to convert between one substance to another using a balance equation. So you have to see the relationship, the mole ratio between the substances in a balance equation. And again, you're swapping one substance to figure out how much another substance. So they're different substances. And that's why labeling not only the units, but also the substance is very important. Let me cross cancel my units as I see appropriate. Okay. All right. Go ahead and work through example 38 on your own and check your answer afterwards. So pause the video to do so. All right, check your answers and make sure you're pretty satisfied with doing this stoichiometry in the methodology of dimensional analysis. So working stoic ratioing using dimensional analysis. All right, so we're getting into stoichiometry, and a subset of this topic is the idea that we have excess or limiting reactants. So how does this scenario play out? If I have 8 car bodies and 48 tires, what we're seeing is the amounts do not fit the ratio. And what ratio are we talking about? It's the 1 to 4 to 1 ratio that we know. So every 4 tires, we need 4 tires for every 1 car body to make a car. And that ratio guides us to know how much products we're going to make, how many cars we're going to make. But we seem to have a lot more tires than car bodies. And we know that if we had 48 tires, we would really need 12 car bodies. But we don't have 12 car bodies. So we call this the limiting reactant, or the limiting amount. And this right here is the excess ER amount. And with that, we can only make 8 car bodies because it's based off of the limiting amount. This limiting amount, there's 8 of them, is going to be the same stoichiometrically, so there's 8 that will be produced. Now, how many car tires are we going to need with the 8 car bodies? Well, 8 times 4, because it's a 1 to 4 ratio, is 32. So we're going to need 32. And how we're going to count it is we're going to do some multipliers, 6 per row, so we're going to do 5. So here's my 5, but then plus 2. So that will give me 32. So 32 tires is how much is going to be needed to fill up these 8 car bodies. Now, how much is left over? There's obviously 12 plus another 4, which is 16. So there's 16 car tires that are going to be left over that are in excess. We call that in the excess amount. So let's go ahead and answer these conceptual questions. Which car part will run out first in this scenario? And it looks like it's the car bodies. And we know that, and the explanation will be verbal. We know that because we don't have enough car bodies to accommodate for the 48 tires. We would need 12 car bodies, but we only have 8, which means car bodies will run out first. Which car part will be left over and how much? And we said it was going to be the tires, and the quantity of tires is 16. So there's 16 tires that will be left over. How many cars can be produced in the assembly line depends on which car part, and it's obviously the one that is limiting, which is your car bodies. So let's look at it in terms of chemistry. In chemistry, when amounts of reactants are not in perfect stoichiometric proportions to the balance equation, one of the reactants will run out first, while the other is left over. The reactant that limits the amount of product is made is called the limiting reactant or limiting reagent, if you want to change up. This is a very old way of naming it. We usually call the reactants the reagents in the laboratory, of course. The limiting reactant is completely used up and first to run out. The excess reactant has some left over, as the excess is not used up completely. The amount of products formed depends on the limiting, not the excess. So let's look at it in terms of a chemistry reaction. Once again, a simple one is oxygen reacting with hydrogen to form water vapor. It's a 1 to 2 to 2 ratio. Now, if I look at these amounts, I want to see if this amount, the reactants, are in a 1 to 2 ratio. If I have 3 molecules of oxygen, I need 6 molecules of hydrogen, and I have more than 6 molecules of hydrogen. So I know that this is going to run out first. This being oxygen is going to be my limiting reactant, and hydrogen is going to be my excess reactant. Now, how much in excess will you see? Well, I'm going to do this problem in a very rudimentary way. For every 1 of oxygen, I need 2 hydrogens. We're really looking at this ratio, 1 to 2. For every 1 oxygen, I need 2 hydrogens. I'm going to show you in a very basic layman terms how this is working. So 1 to 2 ratio constantly. 1 to 2. So I'm going to cross out, and those are all that's reacting. All that's crossed out are what reacts. Okay. And so what's left over is the hydrogen. You can see the excess that's left over. There are 6 molecules of hydrogen that's left over. Now, how much water vapor is going to depend on the limiting, which is oxygen. And notice how each oxygen molecules, there's 2, right? So there's really 6 oxygens. And I know the ratio, if I have 3 of these, I know I'm going to make twice that, which is 6 water molecules. So I'm going to draw 6 water molecules. 1, 2, 3, 4, 5, and 6. Okay, now I'm going to draw my hydrogens. So here's 1. There's my 6. And how much excess is going to be also added to the product side, because I want to conserve my mass between the reactants and products. So I know I have 6 molecules of excess reactant. So far I have drawn 5, and here's my 6th one. So there goes my amounts. I know with the 3 molecules of oxygen, the 12 molecules of hydrogen I started off with, and so now I made 6 molecules of water with 6 molecules of hydrogen that is in excess. So this is my excess amount. Now, so to answer this conceptually, all these questions conceptually, who's the limiting reactant? We know it is oxygen. And we know it's the limiting reactant because it gets used up all completely, whereas hydrogen, only some of it gets used up. Who's the excess? It's hydrogen, and there are 12 molecules of hydrogen. 6 molecules of hydrogen that's left over. And then we go to the last question. How many water molecules did we make? It looks like we made 6 molecules of water vapor. And how we know that is because it's based on the limiting reactant. In other words, here's my molecules of oxygen, and it's a 1:2 ratio, so I know that this is going to make only 6 at most because it's a 1:2 ratio between my limiting and my product. Now, are all problems going to require you to draw out in order to understand what you're looking at? Not at all. So there is a very easy way to determine the limiting reactant, and I'm about to show you using example 39 the quick and easy way to see who is going to run out first. You can do all that in your head, this quick and easy way. Sometimes you'll need a calculator, but for the most part you'll do it in your head. So how do we do limiting reactants? So you're given both reactants, and you're gonna they might be in perfect stoichiometric ratio, and this one actually is a 1:2. So if I have 2 of this, you need twice, and you have twice. So it looks like both of them are going to be my limiting reactants. Now what I like to do is I like to circle my limiting reactants, and I figure out my products from both my limiting reactants. So I'm going to make 4 moles. Notice the perfect stoichiometric ratio. A 1:2 ratio fits really nicely to that 2:4 ratio. There is no excess amount because both of them run out completely. So you're not going to see an excess amount. Okay, now let's go to B. Now B, I'm going to show you again the quick and easy way to figure out your limiting reactant. What I do is I normally just take my reactant, or the amount given to me of each of my reactants, and divide it by their stoichiometric ratio. So that way I know who runs out first. And so 4 divided by 1 gives you 4. 6 divided by 2 gives you 3. And so which one is smaller in amount? It looks like 3 is smaller in amount, so this is my limiting. So I'm doing this all in my head, and you can do it in your head or a calculator to help you to see especially since the numbers are pretty nice anyways. So if this is my limiting reactant, the hydrogen, and the ratio between my product and my limiting reactant, which is hydrogen, is a 2 to 2. That means if I have 6 moles, I'm going to produce 6 moles of water vapor. Now, how much excess? Well, follow along with me as I go through the excess. If I have 2 moles, or for every 2 moles of hydrogen, I need 1 mole of oxygen. So if I have 6 moles here, I'm going to need half that amount. Half that amount of the hydrogen is 3 moles. So I really only need 3 moles of oxygen. So I'm really going to subtract 3 moles, which means I'm going to get a value of 1 mole left over of the oxygen. And I'm going to label my excess to make sure I know who my excess is. Working through the next problem in C, letter C. Once again, I'm going to do the quick and easy way to figure out my limiting reactant so I can focus and figure out my products from my limiting reactant. So if I take 1.0 divided by 1 coefficient, I get 1. 2.5 divided by 2 gives me 1.25. So 1.25 is greater than 1. So I know that the one that will run out first is a lesser amount, which is my 1. The amount of product is going to depend on my limiting reactant. So I'm going to look at my ratio between my product and my limiting reactant. It's a 1 to 2 ratio. So if I have 1 mole right here, 1.0 moles, I'm going to make 2.0 moles of my product. The excess. This is my excess reactant. If I have 1 mole here, I know twice that amount is going to react of my excess because it's a 1 to 2 ratio. And so if I have 1 mole, I know that I'm going to react 2 moles, 2.0 moles of my limiting reactant. And subtracting the amount that reacts from what you have 2.5. The amount that reacts is 2.0, and so the difference is going to be 0.5 moles of hydrogen. So I want you to work through the rest. You'll see me circle all the limiting reactants, and again, the work as I go through each of these, you'll see me work through. The answers are all there, so I'm just going to circle the limiting reactant just to make it easier for all of us, okay? So this is the limiting reactant, and then of course you can calculate the product as well as the excess amount. Your work, and make sure you again understand your conceptually what's happening when it comes to limiting reactants and excess. Alright, we're going to model limiting reactants. We have modeled it already, but we're going to continue modeling and practicing modeling. So we're going to first write a balanced equation for the reaction between hydrogen and oxygen. So hydrogen reacts with oxygen gas to form water vapor. And I know that there's 2 here, and 1 here. So after I write that balanced equation, then I count how many particles are in each of these containers on a microscale. So these are your microscale illustrations. I want you to try to work through this problem on your own. In other words, pause right now. Answers are down here, of course, so you can check your work, but I will put in all the data afterwards. Alright, so go ahead and check your answers to example 40. I want you to also do example 41 independently, and in 41 you want to draw the actual limit or excess inside this container. So draw the product as well as the excess amount. And of course in the reactant I put it all in one circle, so I combine the reactants together into one circle. So see what you will form and how much you would form of each of the substances. All right, go ahead and check your answers. I have the answer key down here. Make sure you understand that you're actually producing 2, 4, 6 carbon dioxide molecules. So there's 6 CO2 molecules and 4 H2O molecules and 2 excess molecules of oxygen. So you're going to see 2 molecules of O2 in excess. So here's my ER. So just like dimensional analysis allows us to convert between units and to do stoichiometry, we're about to look at another a nice easy organizational tool that will help us to do any kind of limiting reactant problem. It helps us to tell a story of who the quantities of the limiting reactant that's used up. It also gives us the quantities that are left over of the excess reactant, and then the quantities of the products formed in a chemical reaction. So this is a very nice way to organize any kind of stoich problem with limiting reactants to be considered. And what it is the word ice, and it's a table. It looks like a table, data table like this, but it means the I stands for initial. So here are your initial amounts. Change is what's reacting, and that's why you see minuses here and plus. Usually your reactants is going to react, so you're going to lose some of your reactants to form your product, and that's why there's a plus here. Your E stands for the word excess, end, or equilibrium. Now, we're not dealing with equilibrium yet, so you're going to see you're going to see us revisit this table later on. That's why it's important for us to really learn how to use this table. And so E really in this case means excess or end. So using an ice table will help organize our information and tell quantities of everything that we would need. So let's begin with this problem right here. You're given initially 10.1 grams of hydrogen and 32.0 grams of oxygen. I'm going to put those two amounts into my initial amounts of both hydrogen and oxygen respectively. Now I'm going to convert between, my stoich can't be done in grams, it has to be in moles. So I'm going to do a conversion between my grams to moles. And my conversion is just a matter of using molar mass. So I'm going to start off with the grams of hydrogen, and I'm going to use the molar mass of hydrogen to calculate my moles of hydrogen. And in doing so, I get 5.00 moles of hydrogen. So I'm going to place that into the box, as you see here. I would also do the same conversion on the side for oxygen. So here's my grams of oxygen, and I'm going to convert that to moles of oxygen. And in doing so, I get my moles of oxygen. These are really nice numbers, and they're purposely nice for a reason. So I put my moles in here. Now once again, you can quickly figure out who your limiting reactant is. Take your amount in moles and divide it by the mole ratio, the molar coefficient, which is 2. So 5 divided by 2 gives you 2.5. 1 divided by 1 gives you 1. So the lesser amount is 1, which means this is our limiting reactant. I like to circle it to focus my attention on that. Now, the initial amount of water vapor is 0 initially, because we haven't reacted to form products yet. So now we're going to see a change occur. Well, I know my limiting reactant is all going to be consumed, so I'm going to lose all of my 1 mole of my oxygen, so minus 1. How much of my hydrogen is going to be twice that amount? So twice that amount is going to be twice 1 mole is 2 moles. So this is how much is going to react. So this is my change. Now I'll figure out that my limiting reactant and my products, the ratio is a 1 to 2, so that twice that amount is going to be formed, and thus plus 2.00 moles. In the end, my amounts are going to look like this. So I'm just going to subtract these values, which gives me 3 moles. And of course, with my limiting reactant, I'm going to see that I don't have anything left over of my limiting reactant. And then, of course, 2 moles is what I form of my product. It's asking us to find the amount of water made. And so all I have to do is look at the moles and convert my moles of water to grams. So I'm going to do that conversion fairly quickly by taking 2.00 moles of water and using the molar mass of water and calculating that molar mass of water to be 36.0 grams of water. Now that mass is in fact what is called my theoretical mass. So this is how much I should theoretically form of the water vapor given my amounts that I started with in this problem. Now let's go to the next problem, or next part of this problem, which is asking us in the previous example how much of excess reactant is left over. And so this table perfectly gives us the amount, and that amount is 3 moles, 3.00 moles of hydrogen, which is in excess. And that 3 moles of hydrogen can be quickly calculated in terms of grams. So 1 mole of hydrogen has a molar mass of 2.02 grams of hydrogen. And so multiplying those values, you get 6.06 grams of hydrogen that's left over. Now, we're going to figure out how Stoich shows for the law of conservation of mass. So my reactants masses are 10.1 grams of hydrogen and 32.0 grams of oxygen. Adding those masses together, totaling that mass, gives me 42.1 grams total of my reactants. Now I'm going to do the same for my products. My product, how much I form is water, and I form 36 grams of that product. But I also have 6.06 grams of hydrogen that didn't react, that's in excess. So I have 36 grams of water vapor. I also have 6.06 grams of hydrogen that is in excess. I add up those values and I get 42.06 grams of my products. Now notice if these two values are pretty close, and they are. And so the law of conservation, mass is conserved between the reactants and the products. But it's important for you to make sure you include that excess in your product for that mass to be conserved. So the excess reactants and the mass of that excess reactant. Let's jump into percent yield. Percent yield is a ratio. It's a ratio of the experimental mass divided by theoretical mass. And usually it's the yield. So yield means product. And so when you're calculating percent yield, it's oftentimes how much you're forming of the product. We said this is the theoretical mass of the water molecule, the product. And so I'm going to put that below right here. So 36.0 grams goes right down here if we're for this particular problem. And that's precisely what we're going to do. The theoretical mass is given, or we know it to be 36 grams of water. Now, experimentally, it says right here, in the previous example, only this much was made in the laboratory. So this is the experimental. And I'm going to write that down. This is your experimental mass. And so let's go ahead and put that ratio together. 27.0 grams of water vapor, times it by 100, just like the equation suggests, and we get 75% yield. So we go into the laboratory, we do the experiment, and we see that this is all that we make because we must have lost some of that water somewhere. And theoretically, we know we should make 36 grams, and so we can figure out what is called our yield and how good our experiment ends up being. A yield of 100% is an excellent experiment. A yield of anything less than 100% means there's errors embedded in the problem. Okay, I would like you to go through example 43. My work is shown here, including my cancellation of my units also. But please make sure you're working through these problems just like I showed you in the previous example. So you've got 2 example sets to work through and make sure that you understand in the end. Oops, I forgot the grams. Here, units. Work through it and check your answers, please, and following up to the end. Now, you want to also make sure you see mass conserved, so work through all the way to this very last example problem. So this ends our full unit 4. It's quite extensive, so make sure that if you need to go back to these parts of these videos, video notes, please do so.